Hello everyone, welcome to Pushp Classes, a free online initiative for GATE, ESE and PSU एग्जाम। हम लोग एक बहुत ही इम्पोर्टेंट सब्जेक्ट दैट इज माइक्रो प्रोसेसर देख रहे थे, तो चले कंटिन्यू करते हैं। थैंक यू।
Now, coming to first chapter of microprocessor. So in this chapter, we are going to look into some basic terminologies. These terminologies are very important for building base of microprocessor. If I talk about GATE exam, then in GATE exam, you will not find questions on these basic terms. But these terms are important if you want to develop a base for microprocessor. And if we talk about ESE or PSU exams, then this topic is very important because you will find that many questions are asked from basic terminologies, and most of the students who prepare for only GATE exam, they are not able to solve these questions because they are not familiar with basic terms. They think that they are familiar, but there's a confusion or doubt in their mind. And when it comes to choosing options, one option from four options, then they generally tend to do mistake. So in this course, we are going to look into the microprocessor from basic to advanced level. So let's start. So first term is, what is computer? So first term is, what is computer? So here, a computer is a machine. A computer is a machine. A computer is a machine. Computer is a machine that can be programmed to carry out sequence of arithmetic or logical operations automatically according to instructions given to it. So, computer is a machine that can be programmed to carry out sequences of arithmetic or logical operations automatically according to instructions given to it. A computer consists of CPU, input-output devices, and memory. So here we can see that a computer has a CPU. This is the main processing unit of computer. It has the ALU, arithmetic logic unit, CU, control unit, and number of registers. Then we have input devices which are connected to it. Some of the examples of input devices are keyboard, mouse, scanner. Then we have the output device connected to it, where we can see the where the outputs are displayed. And some of the examples are like monitor, printer. Then we have memory attached with the CPU. Memories are of two types: RAM, random access memory, and second one is the ROM, read only memory. We are going to see in details this RAM and ROM in later part of this microprocessor subject, or we will see it in much details in computer organization. So when I will take classes of computer organization, then I will discuss these two memory types, and what are the subtypes of RAM and ROM there. So I think it is clear. What is computer? Computer is a machine that can be programmed to carry out number of operations according to instructions which a programmer gives to it. It has a main processing unit, CPU, then it has input and output devices connected to it, and it also has memory connected to it. Okay. Now, what is microprocessor? What is microprocessor? See, if we are able to draw CPU on a single chip, see, drawing doesn't means you are drawing it on pen using pen and paper. Drawing means integrating. If you are able to integrate components of CPU, that if you are able to integrate ALU, CU, resistors on a single chip, and that chip is self-sufficient to act as a CPU, and it is self-sufficient to perform all the functions similar to CPU, then it is known as a microprocessor. So we can define microprocessor. It is a semiconductor component designed by VLSI technology, and it includes ALU, CU and resistors of a CPU in a single package. In a single package. Means what we are doing is we are drawing or we are integrating CPU into a single chip, and that chip is self-dependent and self-sufficient to perform all the functions that CPU is able to perform. Now here one question arises that does microprocessor has inbuilt memory? So its answer is no. Microprocessor doesn't have an inbuilt memory. We have to connect an external memory to microprocessor. That is, if here we are having a microprocessor. See, in this subject, I am going to denote microprocessor with mu p. So don't get confused that what I have written as mu p. So if this is a microprocessor, then we always have to connect an external memory with it. We always have to connect an external memory with it. So I think now it is clear what is microprocessor. In microprocessor, we are when if we have integrated CPU into a single chip, and that chip is able to perform all the functions which are performed by the CPU, then it is known as microprocessor. And does microprocessor has inbuilt memory? No, it doesn't has an inbuilt memory. We have to connect an external memory to microprocessor. See here, some confusion remains in the mind of students. That is, most of the time we say in our common saying that CPU, which is attached with our computer, it is a microprocessor. No, CPU is not a microprocessor. If you are able to draw CPU, if you are able to draw or integrate components of CPU into a single chip, and that chip is able to perform and that chip is able to act like a CPU, then that chip is called a microprocessor, but CPU is not called a microprocessor. So please keep this in mind. We tend to do mistakes in our common saying that CPU is a microprocessor. No, CPU is not a microprocessor. Now, what is microcomputer? So see, what I was saying that this is computer. In computer, the main processing unit is CPU. In computer, the main processing unit is CPU. Now then we saw what is microprocessor. In microprocessor, we are drawing that CPU into a single chip, and that chip is acting like a CPU. Now, if we use that microprocessor or if we use that chip as a main processing unit, and then we connect input devices, output devices and memory to it, then that is known as microcomputer. So what is microcomputer? Microcomputer here's a small spelling mistake. Microcomputer. Microcomputer includes microprocessor as a CPU, and it also has input output devices and memory. So I think now it is clear. When we talk about computer, then CPU is the main processing unit. But if we talk about microcomputer, then CPU is not the main processing unit. Now the microprocessor or the chip, which is developed by drawing components of CPU into a single chip, if that chip act as a main processing unit and it has input, output and memory connected to it, then it is known as microcomputer. So I think now it is more clear to you that CPU is not a microprocessor. CPU is different, microprocessor is different, but microprocessor is able to perform all the functions of CPU. So in common saying, we tend to say that CPU is a microprocessor. But now I think it is clear. In computer, we are using a CPU. In microcomputer, we are using a microprocessor. And what is microprocessor? When we draw CPU or when we draw components of CPU into a single chip, then it is known as microprocessor. I hope it is clear. Now, what is microcontroller? Now, if we are able to draw or integrate microcomputer, this whole part, into a single chip, if we are able to integrate this whole part into a single chip, then it is known as microcomputer, microcontroller. So what is microcontroller? It is microcomputer on a single chip is known as microcontroller. Microcomputer on a single chip is known as microcontroller. So here a question comes, does microcontroller has inbuilt memory? You will say yes. You will say yes. It has an inbuilt memory, because what we are doing is that we are integrating all components of microcomputer into a single chip, and microcomputer has memory in it. So when we are integrating it into a single chip, then we will say that microcontroller has an inbuilt memory. So now let's see some differences between microprocessor and microcontroller. This type of question generally comes in ESE exams. In ESE exam, the problem is that the vastness of syllabus is very large, and questions can be asked from any topic or any subtopic. So, and this type of questions are very favorite for ESC examiners, that they tends to compare between two components. So here we are comparing two components, that is microprocessor and microcontroller. So let's see what it is said, that in microprocessor it contains ALU, CU and resistors. Fine. It also contains ALU, CU and resistors. We have seen it. No internal memory. We have to attach external memory with microprocessor, but it has an internal memory. No interfacing circuit, timers, counters. It has an interfacing circuits. It has timers and counter provisions. It has timer and counter provision. See, microcontroller, here microprocessor, here it is memory. Here we have interfacing circuits, and here we have timers and counters. Now it is used for general purpose application, but it is used for specific purpose application. If we take some example of it, then 8085 and 8086 are examples of microprocessor, and 8051 is an example of microcontroller. Is an example of microcontroller. So students, see, now we can have a quick revision of it. What is computer? A computer has CPU as its main processing part. A computer has CPU as its main processing part. Now, what is microprocessor? What is microprocessor? Now, if we have integrated or if we have drawn components of CPU into a single chip, components of CPU into a single chip, so that that single chip is able to perform like a CPU, then that chip is known as microprocessor. Then that chip is known as microprocessor. Now, what is microcomputer? In this, we are using that chip In this we are using that chip, that is microprocessor, as the main processing unit. Here we are not using CPU as the main processing unit. Here we are using microprocessor as the main processing unit. So it is known as microcomputer. Now, if we talk about microcontroller, if we integrate or if we draw all the components of microcomputer into a single chip, it is known as microcontroller. It is known as microcontroller. So I think now this basic terms are clear to you, and you can easily differentiate between computer, microprocessor, computer, and microcontrollers. Now coming to the next topic, here, see, depending on how data and programs are stored in memory, depending on how data and programs are stored in memory, there are basically two types of architecture. First is known as the von Neumann architecture, and the second is known as the Harvard architecture. In von Neumann architecture, same memory is capable of storing both program and data. Same memory is capable of storing both program and data. But in Harvard architecture, we require different memory for storing program and data respectively. In this, we require different memories for storing programs and data respectively. So depending on how data and programs are stored, there are two types of architecture. One is von Neumann architecture. In this, single memory can store both program and data. And then we have Harvard architecture, in which we have different memories for storing program and data respectively. Now, coming to some basic terms of programming model. Now coming to some basic terms of programming model. So first is, what is program? Program are set of instructions. Set of instructions are called program. What is instructions? It is command. It is command given to a computer to perform a specific task. It is a command given to a computer to perform a specific task. Now, yes. Now, coming to machine level language, assembly level language, low level language, and high level language. Now, let's say it. See, suppose we have an instruction. Suppose we have an instruction, move A comma B. So, the meaning of this instruction is that we want to copy data of B into A. Meaning of this instruction is that we want to copy data of B into A. This format of instructions, are known as mnemonics. This format of instructions are known as mnemonics. Okay. Now see, these mnemonics are partly understood by programmer. Why we are saying like it? See, we are studying microprocessor. Microprocessor is part of our syllabus, so we are studying it. So we are well aware with this mnemonics, that is move A cross B. We know that what is the meaning of this instruction, or what is the meaning of this mnemonics. But suppose there's another student who is not learning microprocessor. Say he is learning something, some other language like C or C++. So, will he remember, or will he know what is the meaning of this mnemonics or instruction? No, it is not guaranteed that he will know meaning of this instruction. So we call mnemonics as they are partly understood by programmer. Now see, this mnemonics we call it as assembly level language. So if we talk about this assembly level language, instructions written in separate word known as mnemonics which are partly understood by programmer. Instructions written in separate word known as mnemonics, which are partly understood by programmer. So this is our assembly level language. Assembly level language. Now see, does microprocessor understand this instruction? No. Microprocessor doesn't understand this instruction because microprocessor only understand binary language, that is 0 and 1, or any code in the form of 0 and 1 are understood by microprocessor. So if we talk about machine level language, what are machine level language? It is a binary medium of communication with a computer through a designed set of instructions specific to a system. Specific to a system. So what is machine level language? It is a binary medium. It is a binary medium of communication with a computer through a designed set of instructions specific to a system. Now what we understood is that we have an instruction. This instruction we call it as a mnemonics. It is called assembly level language and it is partly understood by programmer, but it is not understood by microprocessor because microprocessor understand only binary terms. So what we have done is that we have assigned a binary, we have assigned a binary term to this instruction. We have assigned a binary term to this instruction. Suppose we have assigned it like 0 0 0 1 0 0 0 1. I am just taking an example. It is not that move a comma b is assigned this binary term. I am just saying that we are assigning mnemonics a binary term so that this term is easily understandable by a microprocessor. So now if we feed this input to microprocessor, then microprocessor will understand that what we are trying to say, and then he will take necessary action or necessary steps. So this is known as assembly level language. This is known as assembly level language, and this is known as machine level language. This is known as machine level language. This is known as machine level language. Now see. So you will ask a question that, sir, how we work with microprocessor? So the answer is that first, we write instructions in the form of mnemonics, which is understood by programmer. Okay, as a programmer, we can understand this, we can remember this, and we can write program in the form of this. Suppose we move a comma b, move a comma c, add b. So using all these mnemonics, we can write a program. But if I ask you that you remember all the codes of this mnemonics, and then you write program in the form of this code, then it will be very difficult for you to remember all this code. So for the ease of working, what we have done is that we have designed a mnemonics which is understood by programmer. Programmer writes program in the form of mnemonics. Programmer writes a program in the form of mnemonics. Okay. Then for each mnemonics, a binary term is assigned. It is already assigned. For each mnemonics, binary terms are already assigned. Now, you will ask that, then sir, do we enter this 0 1 on microprocessor? Then answer is no, we don't enter this 0 1 in the microprocessor. Now further what we have done is that we have converted this code into hexadecimal code. We have converted this code into hexadecimal code. we have converted this code into hexadecimal code. So what will be hexadecimal code of this one? It will be 11H. So what we will do is that we will not feed this into microprocessor. Feed in the sense we will not we cannot type this into the microprocessor, we cannot type this into the microprocessor, but we can type or feed this. So as soon as we feed 11H, the microprocessor understand that what we are trying to execute, we are trying to execute move A comma B. So this is the working of a microprocessor. We develop program, programmer develops program using assembly level language, programmer develops program using assembly level language. Then we have assigned binary codes to each instructions. We have assigned binary codes to each instructions. Those binary codes are known as machine level language. Those binary codes are known as machine level language. Then further we have converted this machine level language into hexadecimal code. Again we have converted machine level language into hexadecimal code, and we feed this hexadecimal code into the microprocessor, and then the microprocessor does the desired functions. Now coming to this, what is low level language? Now coming to this, what is low level language? What is low level language? So if we will combine machine level language and assembly level language, then it is known as low level language. If we will assign machine level language and assembly level language, then it is known as low level language. Means low level language are system dependent, or we can say that low level language are machine dependent. Why we are saying it that low level language are machine dependent? It is because see this mnemonics move A comma B, this mnemonics is used only for 8085 microprocessor. Now if we will use 8086 microprocessor, then the mnemonics for this function will be different. If we will use this instruction for 8086 microprocessor, then it will not work. The mnemonics for the same or the instruction for the same function, if we want to implement it in 8086 microprocessor, then there are another set of instructions or another set of mnemonics. That's why it is said that low level language, first, what is low level language? It is combination of machine level language and assembly level language, and it is machine dependent. That is, low level language for 8085 microprocessor is different, and a low level language for 8086 microprocessor will be different. Fine. Now coming to high level language. Languages which are written in English like words, instructions which are written in English like word are said to be high level language. That is, we have seen that instructions of C, C++, Java, they are written in English like word, and they are understood by any people. Understood in the sense that what it is written, the words that are understood by any person. But I am not saying that the codes of C will be understood by every person, that what this code want to implement. But I am saying that the wording of codes are easily understood by any person because they are written in English. Like what like some of the examples we use, that loop, do while. So these are English like word which people can understand. But what loop will do, what do while will do, it is understood by only those persons who are dealing with C or C++. Now the another important feature of high level language is that it is independent of machine. In low level language we saw that it is machine dependent. 8085 is having one set of low level language, and 8086 will have another set of low level language. But for high level language, it is machine independent. See, any code, if we have any code of C++ or Java, then that code will run easily on Windows 7 also, Windows 8 also, Windows 10 also. It is not that one code of C will run on Windows 7 and the same code will not run on Windows 10. So that's why we are saying that high level language, they are independent of machine. They are independent of machine. So now I think it is clear to you what is program. It is clear to you what are instructions. It is clear to you. And if we talk about the machine level language, assembly level language, low level language, high level language, then that is also clear to you. See, this instructions in this form, in the mnemonics form, they are said to be assembly level language, which are partly understood by programmer. Now, when we convert it into binary form, then it is known as machine level language, which is understood by microprocessor. And if we combine both assembly level language and machine level language, then we will get a low level language, and which is system dependent and system specific. And if we have written instructions in a English like word, then it is known as high level language, and they are not machine dependent. So I think this is clear to you. Now, coming to some other terms like compiler, interpreter, and assembler. So this, so see, the function of compiler, interpreter, and assembler is same. What is their function? Their function is that they convert. Their function is that they convert source code. They convert source code to machine code. They will convert source code to machine code. Compiler or interpreter or assembler or assembler. So the function of compiler or interpreter or assembler is to convert source code into machine code. Is to convert source code into machine code. Is to convert source code into machine code. So what is difference between all three? See, what is compiler? It is a software which converts high level language to machine level language. That is, it will convert high level language to machine level language. What is the function of interpreter? It is also a software, and it will also convert high level language to machine level language. Now, assembler, it is a software which converts assembly level language into machine level language. It will convert assembly level language into machine level language. So here we can see the differences between, here the compiler and interpreter are doing the same thing, converting high level to machine level. Assembler is doing a function different from them. It is converting assembly level language to machine level language. So now what is the difference between this compiler and interpreter? See, compiler will convert high level language to machine level language where entire program is converted at a time. Whereas in case of interpreter converts high level language to machine level language line by line. That is, in case of interpreter, one line of instructions will be executed. The error, if any found, will be conveyed to the programmer. Programmer will rectify it, and then interpreter will interpret the next line. But in case of compiler, what it will do, it will execute entire program once, and then total number of errors which are found are conveyed to the programmer at once. and then programmer will rectify the error, and then the program will get executed. So see, what is the advantage of compiler with respect to interpreter? It is time. It is time. Here interpreter is implementing or executing line by line, and after each line it is conveying error to programmer, and then programmer correct it, and then the program moves forward. It will take lot of time, but in compiler the entire program is converted at a time, and if there are any errors, suppose there are 4 to 5 errors, then those 4 to 5 errors will be resolved at once by the programmer. But here, if there are 4 to 5 errors, then the programmer will rectify it 4 to 5 times. So it is so the time involved is less in compiler as compared to interpreter. So we can write it as like this. It is fast, it is slow. It is fast, it is slow. Now see, in compiler, I am not saying that compiler is doing some sort of parallel computing. No, it is not doing any sort of parallel computing. Only thing is that it is executing the program line by line. Here also it is executing the program line by line, but it will execute all the program line by line, and then it will give the result at the end. But here they are executing, interpreter is executing the program line by line, and it is also giving the output to the programmer after each line. So this is the difference between compiler and interpreter. And what is the difference between compiler, interpreter, and assembler we have seen in this. So this all are our basic terms of microprocessor. This all are our basic terms of microprocessor. So I think now you are accustomed with the basic terms. We saw what is computer, we saw what is microprocessor, we saw what is microcomputer, we saw what is microcontroller. We saw the difference between microprocessor and microcontroller, very important for ESE exam. Then we saw type of architecture, von Neumann and Harvard. And then we saw some basic terms of programming model like program, instructions, machine level language, assembly level language, low level language, high level language, compiler, interpreter, and assembler. Now, coming to next part, and that is brief introduction of microprocessor. So here we will see some of the properties of microprocessor. All these properties which are mentioned here, that I am going to take up in details in later part of this course. But here I just wanted to summarize all the points in a single slide, because sometimes some questions are asked from this part in mainly in ESE and PSU exam. So I wanted that you have a gist in a single slide which will help you to memorize it easily. So let's see. The first one is a 8085 is an advancement of 8080 microprocessor. See, in 8080 microprocessor, two instructions were missing, that is SIM and RIM. And these two instructions were added in 8085 microprocessor. So it is said that 8085 microprocessor is an advancement of 8080 microprocessor. Now coming to number of pins, total number of pins in 8085 microprocessor is 40. We are going to deal with the pin description very shortly. There we will study each and every pin in details. Now number of input pins are 21. Number of output pins are 27. So you will say that input and output combining is becoming 48. But here I have told that their total pin is 40. So there must be some sharing or multi-tasking. So the number of pins shared between input and output is 8. This is an important question. It may come in your ESE or PSU exam. That is, total number of pins shared between input and output is 8. Now, Total number of instructions in 8085 is 74. 8085 is a 8-pin microprocessor. 8085 is a 8-pin microprocessor. Why it is called 8-pin microprocessor? That I will discuss in details. Now, if we are having 8-pin, it is not a 8-pin, it is a 8-bit microprocessor. It is a 8-bit microprocessor. It is a 8-bit microprocessor. I will write it here again. Let me cut this part. Yes. 8085 is 8-bit is 8-bit microprocessor. Why we are calling it 8-bit microprocessor, that we will take up shortly. But now you keep it in mind that it is a 8-bit microprocessor. So now coming to the next point, total opcodes in 8085 microprocessor is 246. So you may argue that, sir, you are saying that 8085 is 8-bit microprocessor. So 2 to the power 8, it will become 256. That is, there must be 256 opcodes. So its answer is that in 8085 microprocessor, we have only defined 246 opcodes. So don't get confused with it that 2 to the power 8 is 256. So there must be 256 opcodes. No, it is not like that. Only 246 opcodes are defined for 8085 microprocessor. So if we summarize it, it is an advancement of 8080 microprocessor. 8080 microprocessor didn't have SIM and RAM instructions. Total pin is 40. Input pin is 21. Output pin is 27. 8 pins are shared between input and output. Number of instructions is 74. 8085 is 8-bit microprocessor and total opcodes is 246. Total opcodes is 246. Now, coming to next part, that is number system. Here, number system I have discussed in details in digital part. But here I want some basic knowledge of number system. I want that you must have some basic knowledge of number system. So if there is any student who has not covered my digital course, so you just see this basic part. It will be required in microprocessor. And for more details, you can see my digital lecture. So see, suppose n is our number of bits. So what will be our combination? It will be 2 to the power n, and then we have our range. So if number of bit is 1, then the combination will be 2. For 2 bit, combination will be 4. For 3 bit, 8 combination. For 4 bit, 16 combination, and it will continue so. So for 10 bit, it is 2 to the power 10, that is 1024, that is 1024 combination, and we denote it as 1k. See, k is not 1000 in digital. 1k means 1024. 1k means 1024, and it is equal to 2 to the power 10, and we also denote it as kb, kilobyte, kilobyte, kb, kilobyte. That is 2 to the power 10 is equal to 1024 is equal to 1024 is equal to 1 kilobyte. So what will be 2 to the power 20? It will be 1 megabyte. 2 to the power 30, it will be 1 gigabyte. It will be 1 gigabyte. 2 to the power 40, it will be 1 terabyte. So remember this, it will be used in solving numericals. So what I told, that if n is 10, number of bit is 10, then the combination will be 2 to the power 10, that is 1024, and it is called 1 kilobyte. So 2 to the power 20, it will become 1 megabyte, 30, 1 gigabyte, 40, 1 terabyte. Okay. Now if number of bits are 16, then it will come 2 to the power 16, that is 64 kilobyte, and it will come 65536. See, this figure of 65536 holds much significance in microprocessor, that I will discuss shortly. But here you just remember that 2 to the power 16 is 64 kilobyte, and that is equal to 65536. Okay, I hope that this part is clear to you. Now coming to range. For two combination, range will be 0 to 1, that is it will be 0 and 1. Now for 4 combination, it is range is 0 to 3, that is it will be 0 0 0 1 1 0 1 1. Okay, so my range will become, it is 0 and it is 3. Similarly for 3 bit combination is 8, range will be 0 to 7, and what it will be, it will be 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1. So here we can see that we are having 3 bits. Here we are having 3 bits. Number of combination is 8, and range is 0 to 7. Range is 0 to 7. Number of bits 3, number of combinations 8, and range is 0 to 7. Now similarly for number of bits 4, the combination will be 16 and range will be 0 to 15. So for 4 bits, for 3 bits and 4 bit is important. You will require it frequently in digital and microprocessor. So you should know this sequence. So for 4 bits, what it will come? 0 0 0 0 0 0 0 1 0 0 1 0 0 0 1 1 0 1 0 0 0 1 0 1 0 1 1 0 0 1 1 1 1 0 0 0 1 0 0 1 1 0 1 0 1 0 1 1 1 1 0 0 1 1 0 0 1 1 0 1 1 1 1 0 1 1 1 1 1 2 3 4 5 6 7 8 9 10 11 12 13 14 0 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15. Yes, so here number of bits are 4. If we talk about the combinations, then total combination is 16. Total combination is 16. You can count it: 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16. And if we talk about range, then the range is from 0 to 15. Range is from 0 to 15. Range is from 0 to 15. Now, if we talk about range, then we can see, if we talk about range, then we can see one important thing, and that is the starting range is 0, and ending range is 1. Means I am talking it about in the form of binary. For example, let's see. if we talk about for n is equal to 1, for n is equal to 1, starting range is 1, and see, let me write it like this. This is the starting range, this is the starting range, and this is the ending range. So starting will be 0, ending will be 1. Now if we talk about n is equal to 2, then what will be our starting range? It will be 0, 0, and ending range it will be 1. We saw that for n is equal to 0, range is 0 to 3. That is, it will be, the starting one will be 0, 0, ending one will be 1, 1. Similarly, for n is equal to 3, we will get 0, 0, 0, and 1, 1, 1. That is, the number of bits, here it is 3. So for starting, we will have 3, 0, and for ending, we will have 3, 1. Here number of bits are 2. So for starting, we will have 2 bits, for end 2 0 bits, and for ending, we will have 2 1 bit. Similarly, for n is equal to 4, what we will get? We will get starting 4 0 bit, and then 4 1 bit. So in the same way, if we talk about n is equal to 16, n is equal to 16, so what will be our starting one? Our starting one will be 16 times 0, 16 times 0. You can say it as a starting range. And what will be our ending one? 16 times 1, 16 times 1, 16 times 1. This concept we will use during memory mapping. So keep it in mind. So here we have discussed a little bit of number system. I just wanted to give you a small concept of a number of bits. From number of bits, how we will get combinations, and from combinations, how we will get range, and then from range, how we can get the starting range and the ending range. 2 to the power n is important for microprocessor point of view. It is equal to 1024, and that is equal to 1 kilobyte. And 2 to the power 16 is also important. Why it is important, I will tell you later. And I told you that this figure is important. 65536 is important. In the range, we can also write it as, no, let it be this only, because the rest part I have discussed in details in digital, so no need to cover it here once again. Yeah, if you are interested, then you can see my digital class. Now, coming to next topic, and that is functions of microprocessor. So here I have taken some blocks. The middle block, let's suppose it is our microprocessor. The block in left hand side is denoted as input. The block at right hand side, let us assume it as output, and the block which is below microprocessor, let us assume it is our memory. Now I will take a simple example. From that example, it will be easy for you to understand the functions of microprocessor. So let us assume we have a showroom, a car showroom. Suppose we have a BMW showroom. Suppose we have a BMW showroom. Now let us suppose we have a manufacturing plant, that is the same BMW manufacturing plant. BMW manufacturing plant. Manufacturing plant. Manufacturing plant. So here, let us assume that this showroom is denoted as our microprocessor, or it resembles or it works like our microprocessor. Here, this manufacturing plant works as an input, and suppose our output is BMW customers. Let customers denote our output, and let memory is denoted as the garages or the godam. Write it BMW garage. Yes, fine. Now see, suppose a showroom receives an order of delivering a car. So what will the branch manager of this showroom will do? He will send one of its staff to the manufacturing plant along with the address of this manufacturing plant, so that the staff will bring a car from the manufacturing plant to the showroom. So here we can say it like this: the branch manager is denoted as microprocessor. Microprocessor is sending one of its staff along with an address to the input, and from the input some data will come to microprocessor. Here one thing you have to keep it in mind, that microprocessor or the branch manager is sending its staff along with an address, along with an address, along with an address. This is important. Along with an address, and then some data will move from manufacturing plant, that is our input, to the showroom, that is our microprocessor. Now suppose the car has reached the showroom. Now the branch manager will again send one of its staff to deliver the car to its customer who has ordered that car. And in this time also, the branch manager is going to give an address to the staff where he has to deliver the car. That is again, here microprocessor is sending an address of the output of delivering some data from microprocessor to the output. So here also the thing to be kept in mind is the address. Address is originated from the microprocessor to the output. So in this whole process, that is receiving an order, then sending staff to manufacturing plant, then bringing car from manufacturing plant to the showroom, and then delivering car from the showroom to the customer. What all important points we have learned? What all important points we have learned? The first is, the first important point that we have learned is that address are always originated from the microprocessor for input or output. Address is always address is always originated. Address is always originated. Address is always originated from microprocessor, from microprocessor, from microprocessor for input or output, for input or output. This is the first important thing which we have learned. The second is information flow. The second is information flow between microprocessor and input output is always unidirectional. Information flow between microprocessor, information flow between microprocessor and input output is always unidirectional, is always unidirectional, is always unidirectional. So these two important points we have seen here. See what I told you, that microprocessor or the branch manager will send its staff to the manufacturing plant or the input along with the address of input or the manufacturing plant. Here again, the branch manager or microprocessor will send its staff to its customer along with an address. That is, it will send its staff to the customer or the output along with an address. So address are always originated from the microprocessor for input and output. The second thing we saw that the information flow between microprocessor and input or microprocessor and output is always unidirectional. That is, if we talk about the address, then it always moves from microprocessor towards the input. If we talk of address, then it always moves from microprocessor to output. But if we talk about data, then it will always move from input to, let me erase this. Yes, if we talk about data, but if we will talk about the data, then it will always move from input to microprocessor. And here, if we will talk about data, then it will move from microprocessor to output. That is, in the information flow, we have two things. If here I have written information flow, so I can write it like this also. That is, information flow means two things. One is address, one is address, one is address, and the second one is data, and the second one is data. But even if it is address or even if it is data, the flow will always be unidirectional. That is, for address, the flow will be from microprocessor to input. For address, flow will be from microprocessor to output. For data, flow will be from input to microprocessor. For data, flow will be from microprocessor to output. So I think this is clear to you. Now I will bring memory also in picture. Now suppose the staff of the showroom has brought the car from the manufacturing plant or the input to the showroom, but the date of delivery to the customer is after 2 days. So what will the branch manager do? The branch manager will store this car, that is, the branch manager will store this data in the memory, and after 2 days, the branch manager will again take this car or the data from the memory to the showroom, that is microprocessor, and then it will deliver it to the customer. So what we have seen it here, that here the microprocessor is sending data towards the memory, as well as microprocessor is also fetching data from the memory. That is, here the information flow is bidirectional. That is, here the information flow is bidirectional. So we can write it here, that the third important point which we have seen, the third important point, the third important point which we have seen is that information flow is that information flow from microprocessor to memory, from microprocessor to memory. I will not write it from. From is not the appropriate word. I will write information flow between, information flow between microprocessor and memory is bidirectional, and memory is bidirectional, is bidirectional, is bidirectional, is bidirectional. That is, here we can see that first the car or the data was stored in the memory, and after 2 days the car or the data was again fetched back from the memory. So information flow between microprocessor and memory is always bidirectional, but information flow between microprocessor and input or microprocessor and output is always unidirectional. So I think that now you have understood the working of microprocessor. That is, now you have understood the working of microprocessor. Let me highlight some important terms. Address is always originated from microprocessor for input output. Information flow between microprocessor and input is always unidirectional. And for information flow between microprocessor and memory is always bidirectional. So now if we talk about the functions, if we talk about the functions of microprocessor, so I think that now you can easily say that what all functions are performed by microprocessor. Functions of microprocessor. So the first function is input read. First function is input read. See, this I can say that this function is known as input read. This is input read. Now the second function is output write. Second function is output write. See here, this I can say as output write. See, this I can say as output write. Now third function I can say as memory read, and the fourth I can say as memory write. See here, we can say that this function is known as memory write. We are writing something in memory, and here we can say it as memory read. We are reading something from the memory. So these four functions are these four operations are the main functions of microprocessor. These four operations are main functions of microprocessor. So I think that this example, this showroom example which I have taken, now the functions of microprocessor will be always be in your mind, and you can easily memorize it. That all four functions, what four functions are performed by microprocessor, and those four functions are input read, output write, memory read, and memory write. Now, coming to next topic, that is pin diagram of 8085. So we have discussed it earlier also, that total pins in 8085 are 40. 8085 is made up of total 40 pins. So see, what we are going to do is that we are not going to discuss all the 40 pins of 8085 at one go, because if we do it, then you will not remember each pin of 8085, and it will just get messed up. So what we will do is that we will form different groups of pins of 8085, and then we will discuss each group in detail. We will discuss sub parts of those groups in details. So till the time we complete this course, all the 40 pins will be discussed by me in details, covering all the aspects and all the concepts. And you will also get comfortable with all the pins, and all the pins will be on your tips. So if any question is asked in question, if it is objective, then you can easily solve it. And if it is subjective, that is, if this question is asked in ESE, that draw pin diagram of 8085 and brief it, then you will become so comfortable with it that this will be the first question that you will attempt in your exam. So let's start it. So the first group which I have formed is that first we will discuss about this address bus, that is um, A15 to A8, that is pin number 28 to 21. Along with it, we will discuss this address cum data bus. It is represented by pin number 12 to 19. And then we will discuss control signals like read bar, write bar, and we will also discuss some status signals like input output, memory bar, S1 and S2. So this is my first group. I am going to discuss this all pins in details as a first group, and then we will continue with the other pins of 8085 microprocessor. So first we will discuss about address bus, data bus, and control bus. And then we will look into control signals. Then we will also look into status signals. And then in the later part, we will see that how multiplexing is done in a microprocessor, and the same bus which acts as an address bus, it also acts as a data bus. So we will discuss all this concept in details, and it will be very interesting. You will really enjoy it. So if we talk about the higher order address bus, then what we all are going to discuss, we will discuss A15 to A8. These are known as higher order address bus. These are known as the higher order address bus, higher order, higher order address bus, higher order address bus. See, these all pins are not complete pins of 8085. I have just taken the first group, which I told you earlier that in the first group we will discuss address bus, data bus, control bus, and control signals and status signals. So this is our higher order address bus. Let's suppose this is our lower order address bus, AD7. Why we are denoting it as AD7 to AD0, that I will discuss in details in later part. But for the time being, you just note it down that lower order address bus also act like a data bus. So A for address, D for data. So it is noted as AD7 to AD0. Suppose we write it as lower order address bus, lower order address bus. This all we will discuss in details. The multiplexing part I am going to discuss in details, and I will give you a very important concept, and I will try to make it very simple for you, and you will really enjoy it. That part, which we will take shortly. Address bus. Then we will discuss about some control signals like read bar, write bar, ALE. ALE is address latch enable. We will discuss in details its working. Then we will discuss some status signals like S1, S0. We can add one more here, input output memory bar. So this all pins we are going to discuss in details. Um, we will come into it. Let me first complete it. I will brief this diagram to you in details. Don't worry. Suppose this is my address bus. This is my address bus. This is my data bus. This is my control bus. Control bus. I will come back to this diagram, but first we will discuss address bus. So we have discussed it before also that the addresses, be it for input device, be it for output device, be it for memory, addresses are always generated from the microprocessor for peripheral devices. Addresses are always generated from microprocessor for peripheral devices. So we can define it. Address bus is used to transfer the address of either memory of input output device from the processor. It means address of input output device or address of memory is always originated from the microprocessor. So as I am saying that address are originated from microprocessor, so we can say that address bus are unidirectional. Important. This all questions frequently comes in objective exams. So what I am saying is that addresses are always generated from microprocessor. So address bus are unidirectional. Address bus are unidirectional. Address bus are unidirectional. Okay. Now come into this diagram. So as I am saying that address bus are unidirectional. So this. So what will be the direction of arrow for address bus? It will be here. That is microprocessor is originating an address for input device. For input device. Similarly, address of output device is originated from 8085 microprocessor. Similarly, address for memory is originated from the microprocessor. So we can see that address bus is always unidirectional. Address bus is always unidirectional and it is pointed from microprocessor for peripheral devices. From microprocessor for peripheral devices. Okay. Now coming to other aspects of address bus. If we talk about 8085, then 8085 where there are total 16 address line, or we can say there are total 16 address bus. 8085 has total 16 address bus. Now see, there is a one very important relation between address line or address bus and the memory connected with it. We can write it as this: 2 to the power n is equal to n. 2 to the power small n is equal to big N. Here small n is number of address line or number of address bus. Big N is number of addresses or memory locations or registers required or connected with the microprocessor. So suppose we are saying that in 8085 there are total 16 address bus. So we can write it like this: 2 to the power 16. We discussed it in number system also, where I told you that one figure will be very important for you in future, and now we are going to see that figure. So 2 to the power 16, it will come to be 64 kilobyte, 64 kilobyte, and this figure will come as 65536. So what is this 65536? 65536 is the total number of memory which can be connected with microprocessor 8085. It is total number of memory which can be connected with microprocessor 8085. So if we have the knowledge of address bus, if we have the knowledge of address bus, that how many address bus or address lines are there for any processor, then how many memory can be attached to it, how many memory locations, how many memory locations can be attached to it, we can easily find it out. we can easily find it out we can easily find it out. So I think this is clear to you. So from the so we can conclude one thing, that from address line, from address from address line or address bus, we can conclude we can conclude total memory locations available or connected with the processor, available available or connected with processor, or connected with processor or connected with processor. So this is an important conclusion you should remember. So if we talk about address bus, then addresses are always originated from processor for peripheral devices. That's why address bus is always unidirectional. If we talk about 8085 microprocessor, then it has total 16 address bus or 16 address line. So total number of memory locations which are connected with processor, that we can find it out from a simple formula, that is 2 to the power small n is equal to big N, where small n is equal to number of address line and big N is the number of memory locations which can be connected with the processor. And same we can say that how many registers are also required, that also we can calculate it from the same formula. The memory locations, registers, addresses, number of addresses, all are same. So now let's take some question based on that formula. uh, so here what it is said, a processor has 24 address lines, calculate maximum memory that can be connected. So we very well know the formula, that 2 to the power n is equal to big N, where small n is total number of address line and n is total number of memory locations connected. So in the question it is given that total number of address line is 24 and we have to calculate maximum memory that can be connected. So what it will be, we can write it like this: 2 to the power 4, 2 to the power 20. We can write it like this: 16. 2 to the power 10, I told you, is 1 kilobyte, and 2 to the power 20 is 1 megabyte. So it will be 16 megabyte. So 16 megabyte memory can be connected with this processor having 24 address line. I think it is easy, simple formula. Max memory connected. Max memory connected. Now, if we take another example, a memory of itna terabyte can be connected to a process, find number of address line. So if we write the formula, 2 to the power n is equal to big N. So here big N is given, that is total number of memory locations which are connected, it is given, that is 256 terabyte, and we have to find number of address line. So we can write it easily, 2 to the power n is equal to 256 terabyte. This we can write it as 2 to the power 8. Terabyte is 2 to the power 40. We discussed it earlier also. So it will become 2 to the power 48. So n, that is number of address line, will be equal to n, that is number of address line, will be equal to 48. This will be our answer. Easy. Now coming to another question. Here also total number of memory which are connected with microprocessor is given 100 gigabyte. Now we have to calculate number of address line. So we very well know the formula, 2 to the power n is equal to big N. Okay. So now So now 100 gigabyte, 100 gigabyte, gigabyte can be written as 2 to the power 30, 2 to the power 10 kilobyte, 2 to the power 20 megabyte, 2 to the power 30 gigabyte, 2 to the power 40 terabyte. So see, here we have two options. 100, that is if we take 2 to the power 6 into 2 to the power 30, then 2 to the power 6 will be, it will be 64, it will be 64 gigabyte, it will be 64 gigabyte, 2 to the power 36, it will be 64 gigabyte. And another option is that if we will take 2 to the power 7, 2 to the power 30, then 2 to the power 37, it will be 128 gigabyte. So now you will get a confusion that which one to choose. If we are taking 2 to the power 6, then we are getting 64 gigabyte, which is less than 100 gigabyte. And if we are choosing 2 to the power 7, then we are getting 128 gigabyte, which is greater than 100 gigabyte. Then what will be our answer? So our answer will be this one, that is 128 gigabyte, and the number of address line will be n is equal to 37, because we can afford to have some empty spaces, but we cannot afford to lose data. Here if we will take 64 gigabyte, which is less than 100 gigabyte, then we will lose data. Here if we will take 128 gigabyte, which is greater than 100 gigabyte, then we will have some empty spaces, but it is better to, but we will not lose any data. So it is better to have empty spaces than to lose data. So I hope this question is clear to you. Fine. Now coming to the next bus, and that is data bus. So data bus has multiple role. Data bus has multiple role. It is used to transfer data between microprocessor, memory, and input-output device. See, first let's the second this point also. Data bus is bidirectional. This is important. In address bus, we saw that address bus is unidirectional, but data bus is bidirectional. See, this point, that why data bus is said to be bidirectional, this I am going to discuss shortly when I will discuss multiplexing of address and data bus, and there I will take it there I will take you in depth that what exactly happens in microprocessor, how multiplexing is done in microprocessor, and why data bus is acting as a bidirectional. That there I will discuss in details, but here you just remember that what is the role of data bus. See, I told you that total address line in 8085 microprocessor is 16. So we write it as like this, that is A15 to A8, and then A7 to A0, A7 to A0. This I told you that this is our higher order address line, and this is our lower order address line. Then see, this lower order address line can also be used as a data line. Can also be used as a data line. That's why we also denote it as AD7 to AD0. So what happens is that at one instant, this lower order address line, it act as a address line, and what it does is that it take addresses from microprocessor, and then it gives it to input devices, output devices, memory. That is, it is acting like an address line. It is acting like an address line. Then again, in second instant, this data bus will change its role. This data bus will change its role, and now it will bring data from input devices, from output devices, from memory to the microprocessor. So data bus is doing multitasking, I will not say data bus. I will say that this lower order address bus is doing multitasking. At one instant, it is acting like an address bus, where it is taking addresses from microprocessor, and then assigning it to input, output, and memory devices. And then in the second instant, it is taking data from the peripheral devices and bringing it back to microprocessor. That's why data bus is said to be bidirectional. That's why data bus is said to be bidirectional, because it is doing multi role. At one instant, it is acting like a address bus, and in second instant, it is acting like a data bus. How it is exactly happening inside the microprocessor, that I will discuss in detail, and you will really enjoy that part. But for the time being, just keep it in mind that data bus is used to transfer data between microprocessor, memory, and input output device. Okay. Here data means address and data both. That depends that in which role data bus is acting, whether it is acting like an lower order address bus or it is acting like an data bus. It is bidirectional. Now it is important. We discussed earlier also that 8085 is a 8-bit microprocessor. 8085 is a 8-bit microprocessor. Why it is called 8-bit microprocessor? It is called 8-bit microprocessor because total number of data lines or total number of data bus which is available in microprocessor, it is 8-bit, is 8-bit, is 8-bit. And here I have written it clearly that a processor is identified by the length of a data bus, that is number of bits it can process at a time. That is, if we are calling 8085 as a 8-bit microprocessor, then after learning this concept, if anyone asks you that 8085 is called 8-bit microprocessor, then why it is so? Then you will directly say that it is called 8-bit microprocessor because it has 8 data lines. It has 8 data lines. Suppose we have another microprocessor, XYZ microprocessor. And if someone tells you that XYZ microprocessor is a 50 pin microprocessor, XYZ microprocessor is 50 pin microprocessor, then tell me how many data lines or how many data bus is available in XYZ microprocessor. Then you will simply say that there are 50 data lines or data bus. That's why it is known as a 50-bit microprocessor. So I think this part is clear. Data bus, it is bidirectional because at one instant it act like an address bus, and in second instant it act like a data bus. And in 8085 they are total 8-bit, they are total 8 data lines or 8 data bus. That is why we are calling it as 8-bit microprocessor. And from the number of data lines and number of data bus, the length or the bit of microprocessor is defined. So I can conclude here one thing, that if we have an idea of address line or bus, if we have an idea of address line or bus, then if we have idea of address line and bus, if we have idea of address line and bus, then we can conclude total we can conclude total memory location. We can conclude total memory location. We can conclude total memory location attached with microprocessor. We can conclude total memory location attached with microprocessor. And if we have an idea of a data line or data bus, then we can conclude length of microprocessor. Then we can conclude length of microprocessor. Then we can conclude length of microprocessor. This is important. This is important. Now, coming to the third category of bus, and that is control bus. So what is control bus? So control bus is used to transfer the control signals required for various operation of the processor. So it is used to transfer the control signals and clocks. We can also write control signals and clocks required for various operation of processor. Some of the examples of control signals are ALE, address latch enable, read bar and write bar. Read bar and write bar. See here, we generally get two type of confusion. One is we get confused between control signals and status signals. That which one is control signals and which one is status signal, we get confused with that. So I told you that ALE, read bar and write bar, these are our control signals. And if we talk about the status signals, and if we talk about status signals, then status signals are S1, S0, input output, memory bar. These are our status signals. See, this ALE, read bar, write bar, S1, S0, input output, memory bar, we are going to discuss in details. Don't worry about it. Here we are just defining some things. So I am telling that control signals are three: ALE, read bar, write bar. Status signals are S1, S0, input output, memory bar. Generally the confusion is regarding this. Many times student confuses that this is the control signal and they do mistake in exam. Okay. Then the second confusion is that whether control bus is unidirectional or bidirectional or partially bidirectional or partially bidirectional. We get confusion here that whether control bus is unidirectional, bidirectional, or it is partially bidirectional. Then see, if you are given a question like this, control bus are option A uni, option B bi, option C both. And we have another question. Control bus are, also write this. No. Here control bus are uni, bi, partially bidirectional, D is none. So if you get a question like this, then our correct answer is unidirectional. Keep it in mind. It is unidirectional. But if we have a option which is partially bidirectional, then this will be our answer. I am telling that if you get a question like this where you have uni bi both none, but you don't have any option regarding partially bidirectional, then go for uni. Don't go for none because uni is given. Don't go for none because uni is given. Go for uni. But if you are given a question like this where it is mentioned that it is partially bidirectional, then go for C. Okay. Now, why I am saying that it is partially bidirectional? So coming back to our this diagram, then see, this is our control bus. What is the function of control bus? It is to take control signals from microprocessor and then give it to input, output, and memory. For direction sake, I am showing it as unidirectional. For the direction sake, I am taking it as unidirectional, but it is partially bidirectional. Why it is partially bidirectional? Because after taking control from microprocessor to the peripheral devices, it also gives a confirmation message to 8085. It also gives a confirmation message to 8085. That's why we are calling it as partially bidirectional. That's why we are calling it as partially bidirectional, because it sends a confirmation message to 8085 after it has communicated with peripheral devices. So I hope this is clear to you. So now we will come to multiplexing of addresses and data lines. So see students, till now what we have discussed is that we have discussed some terms, and we have discussed many theory concepts, many theory things we have seen. Now we are going to come into the execution part. Now we are going to deal with the execution part, that how exactly instructions are executed in microprocessor. So now things will become very interesting. I am going to give you number of shortcuts, number of important concepts, and you will have an insight of how microprocessor is actually working. So things are going to become very interesting from now onwards. So just listen to me carefully. Now, coming to next topic, that is multiplexing of address and data lines. Very important topic, very interesting topic, and from here onwards, we will get a look, or we will get an insight of how microprocessor actually works. So please listen it carefully. So first of all, I will try to uh, tell you that what is our overall aim. Our overall aim is that suppose we have a memory. Suppose we have a memory. Address of memory is suppose address of address of memory is suppose 2060H. Okay, we have a memory and the address of this memory location is 2060H. Now microprocessor wants to communicate with this memory, read data which is present in this memory, and then bring that data back into the processor. So basically the aim of microprocessor is reading data from a memory having memory location address as 2060H. So basically what microprocessor want is that it wants to read data present at memory locations 2060H. This is the final aim of microprocessor. We are just taking an example so that we can see that how microprocessor actually works and how basically how multiplexing is done in between address and data lines. So here this is our memory location. This is our decoder. See the functionality of decoder and memory location we will see in details in coming session. But here just you remember that this is memory location. This is decoder. Decoder for time being you just keep in mind that the what is the function of decoder. It is acting as an interface between memory and microprocessor. Microprocessor doesn't communicate with memory directly, it communicates with memory through a decoder. Okay, it is fine. Then here we are having a latch. Here we are having a latch. Here we are having a latch. This module is called a latch. It is an external module which is connected with the microprocessor. It is an external module which is connected with a microprocessor. So what all we have seen? We have seen that we are having a memory location whose address is 2060H. We are having a decoder which is acting as an interface between microprocessor and memory, because microprocessor doesn't directly communicate with memory. It communicates with memory through decoder. Then we are having a latch which is an external memory, which is an external module connected with the microprocessor. And what this latch is containing? This latch is containing D flip-flops. This latch is containing D flip-flop. This latch is containing 8 D flip-flops. This latch is containing 8 D flip-flops. This latch is containing 8 D flip-flops. Then what was our aim? Our aim was that microprocessor wants to communicate with memory location having address 2060H, and it wants to read data which is present in this memory location having address 2060H. Fine. Now see, we discussed it earlier also that there are total 16 address line. There are total 16 address line which we denoted as A15 to A8. This is known as our higher order address line, and then A7 to A0. This was called as our lower order address line. This was called as our lower order address line. We also discussed that there are total 8 data lines in microprocessor. There are total 8 data lines in microprocessor. Now what we will do is that we will try to multiplex this lower order address line and make it as a data line. What we want is that we want to multiplex this lower order address line and mm, make it work as a data line. So we denote it as AD7. So we denote it as AD7 to AD0. A for address, D for data. It is doing multitasking because it will act as a address line as well as it will act as a data line at different occasions. Now see how it is done. So we told that, so I told you that the address of memory is 2060H. So this is our higher address. So higher address will get latched with, so higher address will get latched with our higher order address line. This higher order address line will have 20H. This higher order address line will have 20H and this address will come to decoder. Easy. What I told you, this memory location is having address 2060H. This is our higher bit byte. So it will get latch with our higher order address bus and it will then come to decoder. Now, what will happen with 60H? This is lower order. So it will get latch with our lower order address line. It will get latch with our lower order address line. But what we have done is that we are using this lower order address line as data line also. That is, we are multiplexing it and we denoted it as AD7 to AD0. This is our AD7 to AD0. That is, now this 60H will get latched with AD7 to AD0. This 60H will get latched. This 60H will get latched with our AD7 and AD0. AD7 and AD0. That is here in this portion. What we will have? We will have 60H. We will have 60H. Fine. So, microprocessor originated a memory address. Microprocessor originated a memory address that is 2060H, and this address is the address of memory location with which microprocessor wants to communicate. So 20H gets latched with higher order address bus and 60H gets latched with lower order address bus. Lower order address bus is also used as a data bus. So we wrote it as AD7 to AD0. Now, as a microprocessor originated the address 2060H at the same time, ALE, that is address latch enable bit, also get high. Also get high. ALE will get high. ALE will get high and it will come to latch. When it will come to latch, then this high bit, that is 1 bit, will come to all the D flip-flops and it will energize all D flip-flop. See, what is the property of D flip-flop? That when the D flip-flops are energized, that is when we apply 1 to all the D flip-flops, then its next state will be equal to the data which is present in D flip-flop. So whenever D flip-flops get energized, then its next state becomes equal to the data which is present in D flip-flop. And when D flip-flop is de-energized, then it will restore its previous data. Then it will restore its previous data, and in that case you can write qn plus 1. is equal to Qn, that where Qn is our previous data. So what I told you is that first, the address was originated by microprocessor. At the same time, ALE bit was high. ALE bit was high. This high bit will come at latch. This high bit will energize all the D flip-flops, and D flip-flop has a property that when it get energized, then its next step, and then its next state is the data which is present in D flip-flop. So this 60H data which was present here, which was present at the inputs of all the D flip-flop, it will come to the output of all the D flip-flop, that is it will come to Qn plus 1th state, and this 60H will come here. See what we have at the output of D flip-flop? We are having A7 to A0. What is our A7 to A0? It is our lower order address bus. So we can see it here that 60H get latched to our higher order address bus. This is our higher byte, and the lower byte finally get latched with our lower order address bus. Earlier it was with AD7 and AD0. AD7, AD0 and A7, A0 is not different. It is just that with lower order address bus we are doing multiplexing, so we have noted it as AD7 and AD0. And here it is A7 and A0, that is this will only deal with addresses, but this will deal with addresses as well as with data. How it is dealing with data, that I will show you in a short while. So now this 20H was already present at decoder. Now this 60H will also come at the decoder. Now the decoder will give a single output, and it will energize this memory location. This memory location will get energized. And as read bar was also energized from the microprocessor, this is a control signal, read bar is energized from microprocessor. So it is given command to the memory. It is given command that read operation has to take place, that is data which is present in memory location 2060H. Here this data will be read and it will be brought back to the microprocessor, using this path. Suppose data is suppose data is 20H. So now this 20H data which is inside this memory location will be read, and this 20H data will come back. This 20H data will come back to processor. See, I can write the direction of arrow. This direction will be in this side. This, this, this. This direction will be this side. This direction is this. This direction is this. Here, this. Here, this. Here, this. Now 20H is coming, and this will go inside processor. So we can say that it is bidirectional. It is bidirectional. It is bidirectional. So you will say that, sir, earlier you told that AD7 to AD0 was having 60H, but now but now 20H is coming through this path. So 20H will override 60H. Yes, you are absolutely right. 20H will override 60H. 20H will override 60H. But and this 20H will come inside the processor, and our aim which was to read 20H data from this memory location and bringing it back to processor is complete. Our aim is complete. But see, by the time as I told you that ALE was energized, and after energizing all the diff flops, when the data 60H comes here, then ALE again becomes de-energized. Now here we saw that 20H is overwriting 60H. So what will happen to this data? This 60H data will remain same and it will remain latched between A7 to A0. Why? Because my ALE is de-energized. My ALE is de-energized. So as my ALE is de-energized, it will de-energize all my D flip-flop. It will de-energize all my D flip-flops. And I told you earlier that in the de-energized state, what is the next state of a D flip-flop? It is the previous state. And our previous state is 60H. So this 60H will remain intact here. But here our data has changed from 60H to 20H. So it is clear. So see, here we can see higher order address bus, unidirectional. Okay. See, I told you this is our lower order address bus, unidirectional. But this AD7 to AD0, it is our data bus. It is our data bus. It is bidirectional because at one instant it is taking addresses, it is dealing with addresses, and it is taking addresses from microprocessor towards peripheral devices, and in next instant it is dealing with the data, it is bringing back data from peripheral devices to microprocessor. So it is a bidirectional. So it is bidirectional. So I hope it is clear. If I again revise it, then I am saying that my aim is to bring data 20H, which is present at memory location 2060H, to the processor. So what processor will do? Processor will first originate address 20X H. It will first originate address 2060H. It will first originate address 2060H. This 20H will get latched with higher order address bus, and it will come to decoder. Simultaneously, ALE will get energized. This ALE will energize all my D flip-flops, and as a result, this 60H, which was latched with our AD7 and AD0, this 60H will come here. My 60H will come here at A7 and A0, and this 60H will come at decoder. Then my decoder will energize my memory location, and as control signal read is high, so this data 20H, which is inside memory, will be read, and it will come back to processor in this path. So my this path, that is AD7 to AD0, it is acting both way. If it is acting like a data address bus as well as a data bus. When this 20H is overwriting this 60H here, then this 60H will not be affected. This 60H will remain intact with our lower order address bus, because ALE is de-energized by this time, and as ALE is de-energized, all my D flops will also be de-energized, and it is property of flip-flop D flip-flop that when it is at a de-energized state, then its next state is the previous state. Its next state is the previous state. So this is how we are achieving multiplexing of address and data lines. So you can see that so interesting things are going inside the microprocessor, and how we are using this lower order address line, and we are multiplexing it as a data line and address line. So this all was the working of microprocessor and how it is multiplexing address and data lines. So now you will say one thing, that sir, why we are doing all this multiplexing? Why we are doing all this multiplexing? It would have been better if we had used address line separate and data line separate. Our complete A15 to A0 would have worked as a address line at all instant, and we would have another 8 pins for data lines for as D7 to D0. Then see the problem was at that time the testing bench available to test microprocessor could deal with only 40 pin microprocessor could deal with only 40 pin microprocessor. That is the test bench which was available at that time. It was able to deal with only 40 pin microprocessor. It was able to deal with only 40 pin microprocessor. And if we would have used address line separate and data line separate, then we would have required 24 pins for achieving our purpose of address line as well as data lines. But by multiplexing lower order address line as data line, we are achieving the same function by using only 16 pin. So here we have saved our 8 pin. So here we have saved our 8 pin, and we have to do this saving because the test bench available at that time could deal with only 40 pin microprocessor. So that was the requirement for the multiplexing. So that was the requirement of multiplexing. So again, we are having higher order address bus A15 to A0, lower order address bus A7 to A0. This lower order address bus, we are multiplexing it as address bus as well as data bus, and we have denoted it as AD7 to AD0. Okay. And we can see here that we discussed earlier also that address bus is unidirectional. See, this part is acting purely as a address bus, it is unidirectional. This part is acting purely as a address bus, it is unidirectional. This part is acting as a data bus because sometimes it deals with address, sometimes it deals with data, so it is bidirectional, which we discussed earlier also. So I think now after this much of explanation, it is clear to you that how we are doing multiplexing of address and data lines. What was the role of this latch? What was the role of this latch? This is an external module. This is an external module which is connected with the microprocessor. But we don't have any other option also other than connecting this external module with the microprocessor, because the test bench available at that time was of only 40 pins. So by using this latch module, which is having a number of D flip-flops, we are reducing our requirement of 24 pins to 16 pins by multiplexing this lower order address line. And from here we also saw the functionality of D flip-flop, that what will be the next state of D flip-flop when it is energized, and what will be the next state of D flip-flop when it is de-energized. And then we saw here that how 20H data of memory was overwritten 60H, but this overwriting is having no effect on the address which is saved in the low order address bus, that is A7 to A0. So I hope this part is clear to you. This is very important to understand the functionality of microprocessor and to understand the multiplexing of address and data lines. So now, after this discussion of multiplexing of address and data lines, we can conclude one important result. We can conclude one important result, and that is if ALE pin, if ALE pin is high, if ALE pin is high, if ALE pin is high, then all 16 address line are acting like a address bus. All 16 address line, all 16 address line. All 16 address line are acting as address bus. 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 And if ALE is 0, ALE1 means ALE is energized. And now if ALE is 0, if ALE pin is 0 or ALE is de-energized, then lower order address bus acts as data bus. Lower order address bus, lower order address bus, lower order address bus acts as data bus. Lower order address bus acts as data bus. So this is an important conclusion which you should know. And by this, by energizing ALE and by de-energizing ALE, we are achieving multiplexing of address and data lines. So now we have seen that how we are doing multiplexing of address and data lines. Now we are doing one more multiplexing here. While doing memory read or memory write or input output read or input output write, we are doing one more multiplexing. We are doing one more multiplexing. So let's see. I told you earlier that microprocessor performs four basic function. Microprocessor performs microprocessor performs four basic function. Microprocessor performs four basic function. Microprocessor performs four basic function. One is memory read. One is one is one is memory read. One is memory read. Another is memory write. Another is memory write. Then input output read. Input output read. Input output read. Input output read and input output write. Input output write. See here we are saying that input output read, it's a common terminology which we uses, but reading always takes place from input devices. So if we talk about input output read, it means that microprocessor is reading from input devices. And if we are talking about input output write, then it means that microprocessor is writing into output device. It is writing into output device. Microprocessor cannot read from output device and microprocessor cannot write into input device. So keep this in mind. So in all the four basic functions, we can see that it is a kind of active low signals. It is a kind of active low signals. It is a kind of active low signals. Active low signals. That is in their output. If we have a 0 bit, that is in their, not in the output, in their input, when we will have 0 bit, then only this will be activated. Then only this will be activated. Now see, We can see here that a microprocessor performs four basic functions. So for performing these four basic functions, we would have required four pins, but it is not like that. We can achieve these four basic functions. We can achieve these four basic functions by using only three pins. By using only three pins, and we can achieve it only because there's a very important concept that at a time microprocessor can perform only one function. This is very important. This is very important. At a time, at a time, microprocessor, at a time, microprocessor can perform only one function. Microprocessor can perform only one function. Only one function. At a time, microprocessor can perform only one function. Only thing is that microprocessor performs its function in such a high speed that it looks that it is doing parallel computing. It is performing two, three functions at a time, but it is not so. It can perform only one function at a time. And using this concept, we have multiplexed. We have introduced multiplexing concept in which for performing four functions, we have used only three pins, in which we have a multiplexed selection of input, output, and memory through a single pin. Through a single pin, we can select either input, output, or memory, and here we are doing the multiplexing. And for multiplexing, we have to use external hardware. For multiplexing, we have to use external hardware, and the external hardware used is the NAND gate. External hardware used is the NAND gate. NAND gate has a property. NAND gate has a property that if these are the inputs, if these are the inputs, and this is the output, 0 0 0 1 1 0 1 1, then for 1 1 the output will be 0, and for the rest the output will be 1. We are interested with this 0. We are interested with this 0 because I discussed earlier also that all these functions, memory read, memory write, input output read, input output write, are active low signals. So we require 0 at their output. We require 0 at their output. Only then this will be activated. Only then this will be activated. Only then this will be activated. Now let see a table. Let's see a table, and then we will discuss different combinations. Then we will discuss different combinations. Then we will discuss different combinations. I will write it function. Function. First, let fill it 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1. Okay. Then 0 means it is we are dealing with memory. 0 means we are dealing with memory. Now it is a 0 0. That is, it is reading as well as writing. That is, this functions signifies that we are reading as well as writing from the memory at a same instant of time. So I told you earlier that it is not possible. Microprocessor cannot cannot perform two different functions at a time. So I can write it not possible. Not possible. Not possible. Now coming to here, again we are dealing with memory, and we are reading it. It is one that it is a write will be disabled. So it is a kind of memory read. It is a kind of memory read function. Now coming to this, it will be a kind of memory write function. It will be a kind of memory write function. Write function. Now this here it is 1 1, that is we microprocessor is neither reading nor writing, that is here there is no operation. Here there is no operation. Here there is no operation. Now here again 0 0, that is not possible. If read bar write bar is 0 0, then the function will be not possible, and if read bar write bar is 1 1, then it means no operation. It means no operation. This will be not possible. Now here we are dealing with the input. Here 1, so we are dealing with input. So it will be input output read. It will be input output read. This will be input output write. This will be input output write. And here again 1 1, that is no operation. Here again 1 1, that is no operation. No operation. So this is the table. From this table, if we know the, we can conclude that if we know the inputs at this pins, then we can easily say that which function it is microprocessor is performing. Which function microprocessor is performing. So let's take one, two examples. See, if we will, I told you that this NAND gates are external gates. NAND gates are external gates which we have to connect with the microprocessor to perform multiplexing, by which four functions of microprocessor can be dealt with 3 pins. So we can connect it like this. These are connected like this. These are connected like this. Now read bar, it will come here. Read bar, it will come here. Write bar will come here. Write bar will come here. Now let take one combination. Now let's discuss one combination 0 0 1. Let's discuss 0 0 1. Let's discuss 0 0 1. That is 0 0 1, 0 0 1, 0 0 1. It is 0, it is 0, and it is 1. It is 0. So let's see. Here we will have 0, and here we will have 0. It will become 1 1 1, and it will become 0. That is, we will get memory read. We will get memory read. Now coming to this, here 0 and here 1. Now it will be 0 will become 1 here, and 1 will become 0. It will be ANDed, so it will come it is 0 will become 1, and 1 will become 0, that it will become 0. And if we take again the inverter, then what we will get here? We will get here 1. We will get here 1. We will get here 1. So here there will be no operation because it is active low signal. So we require 0 for it to get activated. Now similarly, if you will continue it for remaining 2, then here and here also you will see that you will get 1 1. So from here also we can conclude that microprocessor at a time can perform a single function. Here if it is performing memory read, then all the remaining 3 functions are deactivated. So I hope this is clear. What I told you is that we are doing multiplexing here also. We are doing multiplexing here also, in which through a single pin we are selecting input, output, and memory. So by doing this, what we are achieving is that all the four functions of microprocessor are dealt with 3 pin, and we don't require 4 pin for 4 functions. So we have saved one more pin here. So the problem which we had earlier, that the test bench has 40 pins, so we wanted to reduce the number of pins as far as possible. So here also there was reduction of 1 pin. Then we have to connect a NAND gate for it. For NAND gate, this all the four functions, memory, read, write, input, output, read, write, are active low. So we want output 0 at the output of the NAND gate. And then we also discussed the different possibilities, where I told you that if it is 0 0 at read bar, write bar, then it is not possible. And if it is 1 1, then it is no operation. Then it is no operation. And by taking this example of 0 0 1, we saw that only one function is performed by microprocessor at a time. So I hope this part is clear to you. Now, coming to the discussion of memory, here we will see what all components are interconnected to form a memory, and how memory works, how we fetch data from memory, and how we feed data into memory, and how this address lines are working, how this address lines are working, how this decoder is working, and what is the functionality of this input buffer, what is the functionality of this output buffer. We will look into it one by one. So we all know, let's start from this side. Let's start from the right hand side. Then we know that memory is a group of registers. 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 So suppose here we are having number of registers. Here we are having number of registers. Here we are having number of registers, and we further know that registers are group of flip-flops. 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 Okay, memory is group of registers. Registers are group of flip-flop. Then suppose each register is having 8 flip-flops. Suppose each register is having 8 flip-flop. Suppose each register is having 8 flip-flops. Suppose we are having total registers. Suppose total registers in a memory is 256. Suppose we are assuming it that suppose total registers in a memory is 256. Okay, and each register has 8 flip-flop. Each registers have 8 flip-flop. Each registers have 8 flip-flop. Then what will be the total capacity? Then what will be the total capacity of memory? Then what will be total capacity? Then what will be total capacity of memory? Total capacity of memory will be equal to 256 into 8 bits. 256 into 8 bits. We know 8 bits is equal to 1 byte. So we can write it as 256 byte. So we can write it as 256 byte. That is total memory. Total capacity of a memory is 256 byte if we are having total registers as 256 and each register is having 8 flip-flop. So we can vary the capacity of memory. For varying the capacity of memory, we have two options. Either we can increase or decrease total number of registers in a memory, or we can increase or decrease total number of flip-flops in each register. So we are having two possibility, or we are having two options to change total capacity of memory. First option is changing the number of registers. If we will increase or decrease number of registers, then our capacity will change of memory. And if we increase or decrease number of flip-flops in each registers, if we will increase or decrease number of flip-flops in each registers, then also the capacity of memory will change. We don't prefer this option. We don't prefer this option. We don't increase or decrease number of flip-flops in a registers, because we know that 8085 is a 8-bit microprocessor. 8085 is a 8-bit microprocessor. 8085 is a 8-bit microprocessor. 8085 is 8-bit microprocessor. So we generally keep 8 flip-flop in one register. So we generally keep 8 flip-flop in one register. So this is how we can calculate the capacity. This is how we can calculate the capacity of memory, considering it considering number of registers and number of flip-flops available in it. Number of registers and number of flip-flops available in it. Then we are having here input buffer. Then we are having here input buffer. What is the role? Whenever a microprocessor want to write data in a memory, whenever a microprocessor wants to write data in a memory, then data will not directly come inside the memory. It will get stored in this input buffer and then it will come inside the memory. Similarly, if microprocessor want to read data from memory, if microprocessor want to read data from memory, then the data which was present here, it will first come to output buffer and then it will go to microprocessor and then it will go to microprocessor. Here we are seeing that we are having two control signals. One is write bar, one is write bar, and one is read bar. One is read bar, one is the write bar, one is the write bar, and one is the read bar. So what will happen? The data will come from microprocessor. It will get stored in input buffer, and when this control signal write bar is activated, then data will come inside the memory. Similarly, when we are reading data from memory, then the data will first come from memory to this output buffer, and when microprocessor activates read bar signal, then the data will move from the output buffer to microprocessor. Here we can see that we are having two control signals, write bar and read bar. That is this memory. This memory we can say it as RAM. RAM is random access memory. That is, we can read as well as write from the memory. That is, we can read as well as write from the memory. If this control bit was not present, only this read bar was present, then we would have called it as ROM. That is read only memory. In that case, we would have only read the data, but we couldn't write anything in the memory. So I think this part is clear. So I think this part is clear. Now see, coming to this decoder part. What is the functionality of a decoder? So I told you that the total capacity of microprocessor is 256 byte. So the input to decoder should have 8 data lines. Input of decoder, input of decoder, input of decoder, input of decoder, input of decoder will have 8 data lines, will have 8 data lines, will have 8 data lines. If we have increased this memory, if we have multiplied it by 2 and it has become 512 byte, then we would have required 9 data line at the input of decoder. Then we would have required 9 data line at the input of decoder. Means I am saying this, that this is not general. That I am saying that I am just taking an example. If I have taken A7 to A0 here, then it doesn't mean that always we have A7 to A0. Sometimes we will find we can get A6 to A0, and sometimes we can get A9 to A0. And similarly, if we are having A15 to A8 here, then doesn't mean that always we will get this. This all things will vary depending upon the capacity of memory. So see, A7 and A0, what is this? These are our lower order address line. These are our lower order address line. So it has 8 lines. It has 8 lines. So it has 8 lines. So total combinations, what will be our total combination? Our total combinations will be 256. 2 to the power 8, that is 256. We have discussed this all in earlier lectures. And what will be its range? And what will be its range? Its range will be, if I talk about in hexadecimal, then it will be from 00H to FFH. 00F to FFH. Okay. So now suppose we are having so how this decoder works. Let's suppose how this decoder works. Suppose here we are having 0. Here we are having 0. That is, our decoder will get energized. We will come here later part. Let us assume that here we are having 0. Here we are, okay, let's start from here only. Let's start from here only. See, this A15 to A8, this A15 to A8 is our higher order address line, higher order address line. Okay. So to get output of NAND gate, to get output of NAND gate as 0, we require A15 and A8 to be all 1. We require it to be all 1. We require it to be all 1. So when it will be all 1, then output of NAND gate will be 0. And in this case, decoder will get energized. Decoder will get energized. Decoder will get energized. See, if I take you little further, then you will correlate all this. See, what I discussed here also, that 20, we were having address 2060H. This is our higher byte. Higher byte get latched with higher order address line, higher order address line, and it directly comes to decoder. It directly comes to decoder. And this is our lower order, this is our lower byte 60H, and this 60H will come in our lower order address bus, that is A7 to A0. It will come from AD7 AD0. I told you how it is coming, but here just to see that our lower order address line is having lower byte address, that is 60H, and then it will come to decoder. So now you can easily correlate. So here, this is our higher order address line. It will have a higher byte of address, and this is our lower order address line, and it will have lower order of address. The function of this is to energize or de-energize decoder. Function of this is to energize or de-energize the decoder, and function of this is to select memory locations. Function of this is to select memory locations. So how we are energizing, de-energizing, I told you that it is A15 and A8 and it is NAND gate. So we required all 1 here, then we will get 0 and it will get energized. Now how we will select address lines, let's discuss here. Suppose we are having something A7 to A0, we are having something like this. We are having this bits. So what will be the role of decoder? Decoder will convert it into binary equivalent. Decoder will convert it into binary equivalent. Decoder will convert it into binary equivalent. So suppose it is 0 0 1 0 1 0 0 0. So it will be 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4, 2 to the power 5, 2 to the power 6, 2 to the power 7. So what we will get? We will get 8 plus 32 means 40. So decimal equivalent of this input is 40. That is 40 number register will get activated. That is 40 number register will get activated or selected. That is 40 number register will get activated or selected, and from there we can either read or write data depending what control signal is available to us. So from there we can read and write data depending upon what control signal is available to us. So here, this is our entire working of memory. This is our entire working of memory. I told you what is the working of this higher order address line. It is to energize, de-energize decoder. And here, lower order address line, it is to select memory location. Decoder helps us in selecting memory locations by converting given input into decimal equivalent. Now I told you what was the function of input buffer and what was the function of output buffer, and how we can call it as RAM and how we can call it as ROM. So now, if suppose anyone asks you that what will be the range, of this memory, Before that, let me show you one more thing. Before that, let me show you one more thing. See how memory are represented. See, this is the descriptive part. This is a descriptive part which I have showed you just for demonstrating and just for teaching you functions of different module. But in general, we don't represent memory like this. We represent memory like this. Here, we will generally have enable pin. Here we will have enable pin. Here we will have read pin if it is ROM, and here we will also have a write pin if it is RAM. Here we will have our A7 to A0. Here we will have A7 to A0, and here will be our, this is our low order address line, and here we will denote our data line, and here we will denote our data line. Here we will denote our data line. Here we will denote our data line. So this is the way. This is the way how we represent memory. Now suppose anyone asks you that what will be the range? Of this memory? So a range of memory we can vary. It is not dependent on microprocessor. It is dependent upon the external hardwares which we are connecting. It will depend upon arrangement of this. It will depend upon arrangement of this. How we are arranging it. What gates we are using here. And depending on that, our range will change. So if you are asked to find range, this is a very important question. For gate point of view. I am going to take number of questions based on this concept, and it is very important for gate point of view. Very important and very frequently asked questions in gate. So if you are asked to find the address, then what you will do? first you will write all the address lines. First you will write all the address line. A15, A14, A13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. See here, if we want to get a 0 at the output of NAND gate, then all this A15 to A8 has to be 1. It has to be 1. See, it has to be 1. It has to be 1. It has to be 1. Now this, see, now coming to low order address bus, I told you that it is 8 bit, so its range will differ from, its range will vary from 00 to FF. Its range will vary from 00 to FF. So what we will do it, we will take our first extreme, that is 00, and then we will take our last extreme, that is 1 1, that is 1 1. So these are our possibilities. So these are our possibility, and here we will always get all 1, because we want output of NAND gate to be 0. If here there would have been some other gate, or here there would have been some other arrangement, if suppose here we would have got a 0 here, inverter here, not 0, inverter, then everything would have changed. Then then the range of this memory would have changed. We will see all this. We will see all this in details when we will solve our questions. But here I am just showing you that what will be our approach while finding the range. So what will be its range? This is all 111, that is FF. This is all 00, FF00, H, and it will go from FF, FF, H. So this will be my range. So this will be my range. So what I told you is that range is not microprocessor dependent. Range is dependent upon the external hardwares and the arrangement of external hardwares which we are using, and along with it, and based on it, our range of memory will change. Range of memory will change. So this was all about our arrangement of memory. So now we will take up some important questions on this memory and on this range concept. We will try to solve all previous year gate questions, and then you will see that how easily now you can solve these questions, and how easily you can find the range. So let's see the questions. Now, before coming to questions, let's see one another important concept where most of you get confused that what will be the result. Suppose we have four arrangement. Suppose we have four arrangement like this, like this, and in this it is given. I'm talking about the enable pin. Most of the time we get confused that when this pin will get activated and when it will not be activated. So what input you have to take for higher order address line or low order address line, depending upon the questions. So we will have four arrangement here. Inverter is here. Here bar is on enable. Here we are having inverter as well as bar. Here we are having inverter as well as bar. And here we are having neither inverter nor bar. So see, if if we are having an inverter, then it is active low. Then it is active low. Here, if we are not having inverter, but we have a bar over enable pin, then this is also active low. then this is also active low. Here if you are not having, if you are having neither inverter nor bar, then it is active high. It is active high. Active low means here input has to be 0 to get it activated. Here input has to be 0 to get it activated. Here input has to be 1 to get it activated. Now this is the disputed part. I will not say disputed part, but here most of you get confused. Here you see inverter and here you see bar, so you think that both will cancel each other, but it is not so. It is also another way of representing active low. It is also another way of representing active low, and it will get activated when we have 0 here. So I think this is clear to you. Now see, let's solve a question. Let's solve a question. We have to find out range of this memory location. We have to find out range of this memory location. Now see, first if we want to discuss the properties of this memory. So here we can see that here we are having memory read as well as we are having memory write. Means here it must there must have been uh, read bar, and here there must have been write bar. So by looking at this, we can say that we are talking about RAM. This is a RAM where we can read as well as write. Now coming to the capacity. Here see, um, A7 to A0, A7 to A0, that is, it is having capacity of 256 into 8 bits, or we can simply say 256 byte. This is the property. Now see, coming to the range. Now see, coming to the range. So first we will write this. Let's take another page. First we will write all this. A15, A14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. First, we will look into the low order address bus A7 to A0. So, let's draw a line here. So, its range will be from 00 to FF. So, first we will fill this 00 to FF. 00 to FF. Now, this part remains the most important thing where you have to apply your brain, and depending on this only the range of this memory changes. Now see what we are having. We are having A15 to A8 here, and we are having an inverter at A8. So what we have to get, we have to get 0 here. When we will get 0 here? We will get 0 here when at this, before this inverter, we have to get a 1, then only it will get inverted to 0. So we have to have 1 here. So to get 1, what all we require 1 1 here, here, everywhere. A15 to A9 should be 1 1, and here we have to put 0, then only it will get inverted and it will become 1, and then here we will get 1, and here we will get 0. So I think this is clear. It is easy. So we will write it like this. At 8 we will get 0 and the rest will be 1. Rest will be 1. So now see the range. What will the range? It will be F. This 4F. This. It is E. And then 0 0. This. And it will be F E F F H. This will be the range. So I told you earlier also that this defines the range. Any modification done here will change the range of the memory. So I think this is clear. It is easy. Now coming to another question. Let's solve another question. So here again we can see Here we are having a decoder. Here address line A15 to A12 are connected. Remaining A11 to A0 are connected. Means what will be the capacity of this? The capacity of this will be 2 to the power 12 into 8 bits, or it will be 2 to the power 12 bytes. We can write it like this also, 2 to the power 2 into 2 to the power 10 byte, and it will be 4 kilobyte. Memory is 4 kilobyte. Here we can see that we can do only memory read. Here we can do only memory read. So it is a kind of ROM, read only memory. Okay. So now what it is saying, this address line is from A11 to A0. So its range will also vary from 00 FF. So we will see it later. Let's come to here. So to enable this decoder, we want 0 here. To enable this decoder, we want 0 here. So A15 will be 0. A15 will be 0. Then only it will get enabled here. Now O naught is coming here. So to enable this, O0 has to be energized. To enable this, O0 has to be energized. So how can we energize O0? See, this is O0. Suppose this is O1, O2, and this will go on. O3, O4. So if we want to energize O0, so we will require 000 here. If we would have required to energize O1, then what we would have put? We would have put as 001. 001. It will go up to O8. It will go up to O8. Suppose this line would have continued from here. This line would have continued from here. Then here we would have got 111. 111. For this is simple. This all we have seen also in digital. This all we have seen also in digital. So I think that you can easily correlate. You will not get confused. Very simple, basic digital concepts. So we require O0. So we will have to put 000 here. If we would have required O8, then we would have put 111 here. So let's come to its range. Again, we will write A15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. A11. So this. So let's put 000 here. All will be our 0. Let's put 111. 1, 1. Okay. Then A15 to A, this all will be 0, 0, 0, 0. 0, 0, 0, 0. So what will be the range? The range will be 0, 0, 0, 0, F, and it will be 0, F, F, F. Not F, H will be H. 0, F, F, F. So this will be our range. This will be our range. This will be our range. So I hope this is clear to you. Only difference we are getting it here. We have used 3 cross 8 decoder. We have used 3 cross 8 decoder, and to energize it, or to activate this, we have to energize O0, and for O0 we require 000. If here we would have got O8, then it would have 111. If it has if we want to if it has been connected by this O1, then we would have put it here 001. And A15 active low, so we require 0 here to get it energized. I hope this is simple to you. So these are some questions. So these are some questions which we have seen, and now I think that your concept must have been clear, that how we find memory locations, how we find memory locations. So now we will take another pattern of question which is generally asked in gate. Most of the time they give this type of questions, and then they try to play games with the mind of a student. So I will take that question also, so that everything will be clear for you. Now, coming to one more question based on finding the memory range. So here we are asked to find a memory range of these three memory. We are asked to find memory range of these three memory. Suppose I call this one as memory 1, I call this one as memory 2, and I call this one as memory 3. So we have to find memory range of this three memory. So see what all are given. Let's suppose we started from here. We have to find out it is RAM or ROM. See, RD bar is given, that is, this one is ROM, read only memory, read only memory. If I talk about this, then here also RD bar, so this is also read only memory. Here we can find RD bar as well as WR bar, that is read in write in, both is possible. So this is our RAM, random access memory, random access memory. Okay. Now come in to the capacity of this memory. So here we can see that address line A12 to A0 are connected. A12 to A0 are connected. Means we can write it as 2 to the power 13, 2 to the power 13, and as each register is having 8 flip-flops. So this 2 to the power 13 into 8, we can write it as byte. We can write it as byte. And what it will become? It will become, this is not byte, this will be bits, because into 8 is there. Into 8 is there, so it will be bits. It will be bits. It will be bits. So finally, it will come out to be 8 kilobyte. It will come out to be 8 kilobyte. I think now this all things are clear to you, but still I will explain you once more. 2 to the power 13 into 8 bits. If I will consider bits, and if I want to convert this bits into bytes, then I can say it is 2 to the power 13 bytes. 1 byte is equal to 8 bit. Then I can further break it into like this: 2 to the power 3 into 2 to the power 10 byte. 2 to the power 10 is kilobyte, and 2 to the power 3, it will come out to be 8 kilobyte. So I think now it is clear to you. So similarly, here also address line A12 to A0 are connected. So this will also be our 8 kilobyte. So this will also be our 8 kilobyte. Here A9 to A0 are connected, means 2 to the power 10 cross 8 bits. So it will come out to be 1 kilobyte. So it will come out to be 1 kilobyte. So I think up to now it is clear. See, this all things you are not asked to find, but still I am giving you an idea that how to read or understand properties of memory. It may come as an objective question. They may give you this block diagram of memory, and they may ask you that whether it is RAM or ROM, or they may ask you to find out its capacity. Our real problem, and that is to find the range. I will come in. I will come to it in later part. So here we have data lines. Here we have data lines. Data lines will be D7 to D0, D7 to D0, D7 to D0, D7 to D0. Now here, this is our 3 cross 8 decoder. This is our 3 cross 8 decoder. At inputs, we are having A12, A11 and A10. A12, A11 and A10. Now, its output is coming to this memory. So this memory will get enabled at O0. O0 means A12, A11, A10 will be my 000. Then this memory will be enabled. Now coming to this is also 3 cross 8 decoder, and here we are, the address lines are A15, A14, A13. Now its one output is coming to this memory, so this memory will be enabled when its output will be O0, that is input must be 000, and one output is coming to this decoder. So this decoder will get enabled when its output is O4. Its output is O4. So I write it like this: 000, 001, 010, 011, 100. See, this all I am writing for your ease to understand it. When we will do question, then we will not write all these basic steps. This must be kept in mind only. This is my 0, this is my 1, this is my 2, this is my 3, this is my 4. So to get O4, we require 100 here. Now similarly for O7, we will O7 will come here. That is, this memory will get energized when O7 will be my output. When O7 will be my output. When O7. So this is the way that we understand a given question. First, we try to understand the arrangement which is given, and then we should proceed for the solution. Because if we start the solution first and then we start understanding the arrangement, then you will get confused and you will commit mistakes. So whenever a questions like this is given, where you have a very big architecture and connection, then you just understand that how everythings are connected and how everything's are connected, and then proceed. Then it will become very easy. Now see, it will become very easy. If we want to find the address, I will start with this one. I will first find the address of this third number memory, then second number memory, then first number memory. So see, I told you that if you want to find the address, then first write A15, all the address line, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Now see here, what are the address lines connected with this? A12 to A0. A12 to A0. So my A12 to A0, first write it as all 0, because the range starts with all 0, and then write all 1, because the range ends with all 1. Simple. Now see, this will be enabled when O7 of this decoder will be enabled. And when O7 will be enabled, when its input will be 111. When its input will be 111, then O7 line will get enabled, and this will come and it will enable this one. So Right, A15 to A14, 1, 1, 1, 1, 1, 1. So this is my address range of memory number 3. Now you can find it in hexadecimal form. I am not going to do it, that you can do it easily. Now coming to the second one. Here also A12 to A0 are connected as address line. Suppose take the memory 2. So here also we will get all 0. Here also we will get all 1. Now coming to the main part. See, this will be enabled when O0 of this decoder will be enabled. And when this O0 will be enabled, when we will get 000 here. When we will get 000 here. When we will get 000 here. Now, write 000 000. Now you will get the memory range of M2 also. Now, coming to M1. Let's see. M1, the number of address line is A9 to A0. So A9 to A0. So here I will write first all 0 and then I will write all 1. Then I will write all 1. Now see, this will be enabled when O0 of this decoder will be enabled. And this O0 will be enabled when we will have 000 here. We will have 000 here. We will have 000 here. Okay. So A12 to A10, 000, 000. Now see, this decoder will be enabled when O4 of this decoder is enabled. This decoder will be enabled when O4 of this decoder is enabled. When will O4 become enabled? When we will have 100 here. When we will have 100 here. 100 here. So write it here. 100. 100. Convert it into hexadecimal, you will get the answer. So this is the way you have to find the memory locations if there are more than one memory locations given. So they see this type of questions become so easy if you are able to understand first the architecture and the connection. These type of questions are very favorite for GATE exams and it is very scoring also. In GATE you will not get this complete arrangement, you will get one or two, but in yes conventional you can get the complete arrangement. So I told you earlier also that first try to understand the arrangement, first try to understand the connections, first try to understand what the question is asking you, and then proceed for the solution so that you will get right answers and you will not commit silly mistakes. So I hope this part is clear to you. Now we will discuss a very important concept, and that is fold back memory or mirror memory concept. Fold back memory or mirror memory concept. Let's see what it is. Many questions are asked in GATE exam based on this concept. So this is a favorite topic for GATE exam. So let's see what it is. So here also we have to find the memory range of this memory. We have to find memory range of this memory. This is a 3x8 decoder. This is a 3x8 decoder. This will be enabled when O2 is enabled. This will be enabled when O2 is enabled. So let's see how we can find its range. So for range, I told you first write all the address line A15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. This is all our addresses. Now see what it is in the memory. What are the address line connected at the input? A10 to A0. Okay, A10 to A0. Put it all 0 here. Put it all 0 here. Then put all 1 here. Then put all 1 here. Easy. Then this will be enabled when O2 will be enabled. For enabling O2, what we require, this is A14, A12, and in mid there will be A13. So we know if we write the combinations as this: 0 1 0, 0 1 1, 1 0 0, 1 0 1, 1 1 0, 1 1 1. So this is 0 1 2 3 4 5 6 7. So we want O2. O2, for O2 it has to be 0 1 0. It has to be 0 1 0. 0 1 0. 0 1 0. 0 1 0. Now A15, for enabling it, A15 has to be active low. So A15 will be 0 0. See, now all are completed. You will say that all are completed. Now we will find the range. No, all are not completed. See, A11. Do we have any information of A11? Do we have any information of A11 in this diagram? No, we don't have any information of A11 in this diagram. Then what we can do with A11? So if we are not given any information of A11, then A11 can take two values. Then A11 can take two values, either 0 or 1. We don't know which value it can take. So we are taking its two values, 0 and 1. So let's see. First we will start with 0. Let it is 0. Let it is 0. Okay, fine. Suppose here also I am just writing it for A11 because rest all will remain the same. Rest all will remain the same. I am only taking the A11. So I told you that if nothing is given of A11, then we will take A11 as either 0 or either 1, and we will get two different ranges for it. We will get two different range for it. So let me write it again, otherwise you will get confused. A15, 14, 13, 12, 11, 10, 9, 8, 0. Okay. So now I told you A11 can take both value. It can take either 0 or either 1. So here I have taken 0. Now see, now try to find out the range. Now try to find out the range. So what will be its range? 0 0 0 0 0 0 0 1 0 0 1 0 0 1 2 2. Okay. If we take a pair of 4 4 4, if we take pair of 4 4 4, so its range will be 2 0 0 0, and here it will be 2. This will be 7. 0 triple 1, 0 triple 1 will be 7. 2 7 F F. This will be the range. This will be the range. This will be the range when A11 has taken value 0. This will be the range when A11 has taken value 0. Now suppose if A11 has taken value 1. If A11 has taken value 1, so what will be our range here? This part will remain same. This part will remain same. Here also this part will remain same. This part will remain same. And in A11, I told you that A11 can take two value. It can take either 0 or 1. So 0 part we have covered here. So we have to take one part here. So now we have to find the range. So what will be its range? 0010, again 2. 1000 means it will be 800H, and this is a lower range, and the higher range will be 2FFFH. So this will be the range. That is, for this memory arrangement, we are getting two range. For this memory arrangement, we are getting two range because nothing is mentioned of A11. Because nothing is mentioned of A11. So as nothing is mentioned of A11, so it can take either 0 or 1. So we have to find range once by considering 0 and then another one by considering 1. So this is the concept of fold back memory or mirror memory range. This is the concept of fold back memory or mirror memory range. Easy, I think you are able to understand it. Now suppose in this A11 was not given. Suppose you will get another question in which you will get A11 and A10 both are not given. A11 and A10 both are not given. So see what all combinations can be there. There can be, it can have either, it can take value either 00 or 01, 10 or 11. That is, there are four combinations. There are four combinations. When one was not given, when only A11 was not given, then there was two combinations. When two is not given, A11 and A10, when nothing is defined of the address line A11 and A10, then there are four combinations. 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 That is, there will be four range. We will get four range. We will get four range. And I think you can easily find out that how you can find the range. See, here A11 was not given, so we took here first we took 0 and then we took 1. Suppose A11 and A10 was not given here. Suppose A11 and A10 was not given here, then first we would have taken it as 00. Here 00. Okay, then we would have found the range. Then we would have taken it as 01. 01. Then we would have found the range. Then we would have taken it as 10. 10. Then we would have found the range. Then we would have taken it as 10. 10. No, not 10. Here we would have taken it as 11, 11, and then we would have found the range. So we would have got four combinations and we would have got four range. Now if suppose we A11, A10 and A9 are not given, then what all combinations we will get here? We will get 8 combinations. We will get 8 combinations. We will get 8 combinations, that is we will get 8 range. That is we will get 8 range. So if I summarize it, then if 1 is missing, if 1 is missing, then it will be 2 to the power 1, 2 range. We will get 2 range. If two address lines are missing, then number of combinations, combinations will be 2 to the power 2, that is 4 combinations or 4 range. Similarly, if suppose n address lines are not given, then we will have 2 to the power n combinations and or 2 to the power n range. Then we would have 2 to the power n combinations or 2 to the power n range. Important. This is the concept of fold back memory. or mirror memory range. That if we don't have any information of one address line, then we will get 2 to the power 1, that is two combinations or two range. If two address line is not given, then there will be four combinations, four range. If n address lines are not given, then we will get 2 to the power n combinations or n 2 to the power n range. Now here, so here this we got when A11 took value as 0, first one. So this is our main range. This is our main range, and this was the range when A11 took value, when A11 took value as 1. When A11 took value as 1. So this will be my fold back range. Fold back range or mirror range. This is my main memory range. This is my main memory range. This is my fold back memory range or mirror memory range or mirror memory range. Similarly, if I talk about this, then this first combination will be my main memory range. First combination will be my main memory range, and rest will be my fold back memory range. Then we will have fold back memory range. Similarly here, the first one we will call it as main memory range, and this we will call it as fold back memory range. So I think now it is clear. If you get such type of arrangement where some address lines are missing, then you should know that it's a concept of a foldback memory or mirror memory range. Then you have to proceed in this way. Then you have to proceed in this way. You have to find out the number of combinations which are possible with missing address lines, and then you will find that number of ranges. And then in the question, if it is asked that what will be the main memory range, then the first combination will be my main memory range. And if question in the question it is asked that what will be my foldback memory range, then the remaining ones will be my foldback memory range. So I think this concept is clear. Very important concept it is for gate point of view. Generally, they tend to give questions on this, and in that case, you will get more than one memory range. I hope this is clear to you. Now, coming to memory mapped input output. Now, coming to memory mapped input output. Let's see what happens here. So here we can see we are having 16-bit addresses A15 to A0, 16-bit addresses A15 to A0 connected with NAND gate, and when its output will be 0, then this will be enabled. Then this will be enabled. So you will say that, sir, it's a 16-bit address. Sir, it's a 16-bit address, and here we have already written memory read. It means that this is a memory. This is a memory. But I will say no, this is not a memory. This is a input device. I will say this is not a memory. This is an input device. And I am enabling or activating this input device using 16-bit address using NAND gate. Can I do it? Why not? See, I have a input device. I have a input device. I just need to enable it. I just need to enable it. For enabling it, I have a two way. Either I can use a 8-bit address, either I can use a 8-bit address, or I can use 16-bit address. Who can limit me? Only thing is that my ultimate aim is that my input device must get activated, and for activating it we can use either 8-bit address or we can use 16-bit address. Anything we can do, anything we can do. Okay, now it is clear. So I am saying that it's an input device, and I am enabling it with a 16-bit address, and I am enabling it with a 16-bit address. Okay, but microprocessor is not knowing that it is an input device. Microprocessor is not knowing it's an input device. Microprocessor will treat it as memory device only. See how? Suppose we have an instruction LDA 16-bit address, and let the address be FFFFH. We will look all these instructions in the coming session, but till now just you know that what is the meaning of LDA 16-bit address. It means that it states that load accumulator with data present at 16-bit address. Meaning of LDA 16-bit address is that load accumulator with the data present at 16-bit address. So when we give these instructions to microprocessor, then microprocessor understand that it has to communicate with a memory location. It has to communicate with a memory location, and no, it has to communicate with a memory. It has to communicate with a memory, and then further it has to pick data which is present at memory location FFFF of memory, at memory location FFFF of memory. So what microprocessor will do? Microprocessor will generate 16-bit address. FF will come at higher order address line, and this will come at A8, and combining this will this FF lower bits will come at lower order address line. So my this the input of NAND gate will have FF FFH. So its output will become 0, and this my input output device will get enabled. It is my input output device, but for microprocessor it's a memory, because I have given an instruction LDA. LDA means that it has to communicate with memory. Fine. So now it has to read data. So it has to read data from memory. So it will generate memory read control signal. It will generate a memory read control signal. So here we will get 001. When 001 will be activated, then this my control signals will get activated. My control signals will get activated. Now the data which is present inside the input device will get copied, and it will come back to the microprocessor. It will come back to the microprocessor. So see what I am saying. I am performing LDA operation. I am performing LDA operation. Meaning of LDA is that we have to load accumulator with the data which is present at 16-bit address. So if we will input this instruction to microprocessor, the microprocessor has to perform two things. It has to first generate 16-bit address. Here the address are generated, and then a microprocessor know that it has to communicate with a memory, so it will generate memory read control signal. But actually I have connected an input device here, and the data which we are copying, that data is copied from an input device. Now you will say that why we are doing it. You will say that let's suppose, we will come to it later. Suppose we have another instruction STA. So STA means store data of accumulator in memory location FFFF. We have to store data of accumulator at this memory location. So in this also, microprocessor will first generate this memory address. Memory address will be generated, and then this time it has to perform memory write operation. This time it will perform memory write operation. This time it will perform memory write operation. So here we will get something like this. Here we will get something like this. Now memory write pin will be activated and we can write data here. So this two functions are implemented. These two instructions are implemented. Now you will say that, sir, why we are doing it? Why we are doing it? Why we are fooling microprocessor by connecting input output devices? And this time when we will perform memory write operation, then it will become output device. It will become output device, not become it means that we have connected an output device and we are fetching and we are feeding data to output device. So you will say that, sir, why we are doing it? Why we are fooling microprocessor by using instructions which are memory related, but actually connecting input output devices. So when we discussed peripheral mapped input output, so we saw that there was 8-bit address line, that is microprocessor could generate 256 addresses each for input and output. 256 addresses each for input and output. Each for input and output. But by this arrangement, by using 16-bit address, microprocessor can generate 65536 addresses. 65536 addresses, each for input and output. Each for input and output. Understand it carefully. Each for input and output. So here, the number of addresses which microprocessor could generate, or the number of memory locations, or the number of input output devices with which microprocessor can communicate, was only 256. But now here the number of input output devices with which microprocessor can communicate is 65536 devices. So this is the advantage of memory mapped input output. So this is the advantages of memory mapped input output. So this is the advantage of memory mapped input output. Now here we can see one more thing, that in a peripheral mapped input output, we were using control pins as input output read and input output write. But in memory mapped input output, the control signals which we are using is memory read and memory write. See, this all are objective questions. I will summarize it, but this all are objective questions which will come in your GATE as well as in your ESE exam, or also in PSU's exams also. In GATE you don't find much weightage of microprocessor, but in ESE and PSU you cannot even imagine of clearing those exams without microprocessor. See, earlier were the days when people used to skip microprocessor. Still, they used to get selected. It was around 10 to 12 years before. But at that time, the issue was that if one student is skipping microprocessor, then rest all are skipping microprocessor, because there was no one, not many good faculties who can teach microprocessor the way now you are taught. So if everyone is skipping microprocessor, then it doesn't affect the output. It doesn't affect the result, or it doesn't affect the cut off. Sorry. But now you cannot imagine of skipping it, because now everyone is studying microprocessor, and so study it nicely. See. Now coming to another concept of memory mapped input output. Let's see another and the last concept. After this, this topic of peripheral mapped input output. and memory mapped input output will get over. Now suppose I am saying that this is my input device. This is my input device, but I am using 16-bit address and I am using a memory read control signal, and I will fetch data from input device, considering it to be a memory device. Considering it to be a memory device, that is, I will fool microprocessor using LDA operation that this is a memory device, but it is actually an input device. Similarly, here I will fool microprocessor that using STA instruction that this is memory device, but it is actually output device where we are using memory write control signals and using 16-bit addresses. And why we are doing it, I told you that the number of addresses will be or the number of input output devices with which we can communicate increases in memory map with respect as compared to peripheral map. So this is an memory this is memory mapped operation. This is memory mapped operation. This is also memory mapped operation. This is also memory mapped operation. Now see, come in here. Come in here. This is my memory. This is my memory, and here I can memory read as well as memory write. That is, it is a kind of RAM. It is a kind of random access memory. Now see what will happen. Suppose we have address FFFFH. Okay, we have address FFFFH. Now what microprocessor will do is that microprocessor is connected with this also. 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 That is FFFF. H will come here also, here also, here also. So first, if we will talk about this and this, then even if FFFFH is here, available here and available here, then also at a time both this input device or output device will not get activated because of this control signal. At a time we will either do memory read or we will either do memory write based upon the input to this control pins. So we can conclude from here that address of this input device and address of this output device can be same, which we have discussed earlier also, that 65536 addresses are generated for microprocessor, each for input device and output device. Now see what will happen here. Here also FFFFH is available here, higher bits in here, lower bits here. But here there will be a problem because here we are having memory read also, memory write also. So there will be confusion that which one will be selected. This will be selected or this will be selected. So this confusion is eliminated by keeping one condition in mind, that memory addresses of input or output devices can never be same with the memory locations of memory device. For suppose if with 2 to the power 16 combination we have 65536 addresses can be generated. 65536 addresses can be generated, and suppose if we have used 5536 address as memory, we have used 5536 address as memory, then the addresses available for input output device is only 60,000. Is only 60,000. 60,000 address. 60,000 address is available for input output device. Is available for input output. So what I am saying is that input device, memory of input device and memory of output device can be same because we are differentiating input and output by memory read and memory write control signals. But address of input device or output device can never be same of that of memory device, otherwise there will be confusion that which one will be selected. So if we are using 5536 addresses as memory, then only 60,000 addresses are available for input and output device each, and not 65536 are available. So I hope this concept is also clear to you. So now let summarize some of the properties. Let's summarize some of the properties of memory mapped input output. Very important concepts I have told you. So just go through both peripheral and memory mapped again, and everything will be clear. So what I told you here, microprocessor will generate 16-bit address. It will generate 16-bit address. Second, memory read and memory write control signals are used here. Control signals are used here. Whereas in a peripheral, input output read and input output write were used. Here 65536 addresses are available are available for input and output device respectively. This is the advantage of memory mapped with respect to peripheral mapped. With respect to peripheral mapped, here instructions used are SDA, LDA. There are other instructions also which are related with memory will come under memory map. But here STA and LDA, there we were using in and out. And here we can write one another thing that memory address of input and output device can be same, but memory address of input output device and memory device can't be same, because then we cannot differentiate that which one will get activated. So see, this all are properties of memory mapped input output, and we have earlier seen the properties of peripheral mapped input output. So this was all important concept of both this mapping. So I think that it is clear to you. Now we will look into another important concept, and that is peripheral mapped input output, peripheral mapped input output, and memory mapped input output. This topic is also a favorite topic for GATE and ESE exams, in which you will get many theory questions based on this topic. And the problem is most of the students don't even have knowledge of these topics, and if they are having knowledge, then they have half cooked knowledge. So whenever they find a question based on peripheral mapped input output and memory mapped input output, then they generally tends to do a mistake. So here we will look both this peripheral mapped input output and memory mapped input output in details. We will look into all the properties of this both kind of types of input output mapping, and then all your doubt and queries will be resolved. So let's start. So first we will deal with peripheral mapped input output. First we will deal with peripheral mapped input output. In our previous discussion, we have seen it. We have seen it. Where we have seen it? We have seen it when the microprocessor was dealing with input-output devices. When microprocessor was dealing with input-output devices using in and out instructions, then there we saw peripheral mapped input output. But let's see it again. In details. So suppose microprocessor wants to communicate with a with an input device and read data from an input device so we discussed earlier also that for this we will use instruction in instruction. By using in instruction, microprocessor can read data of input device. And let's suppose we have an 8-bit address. Suppose we take it as in FFH in FFH. Then what is the meaning of this instruction? The meaning of this instruction is that microprocessor wants to read data which is present at memory location FFH in input device. Okay, then let's see how it is done by macroprocessor. So it's an 8-bit address. So this 8-bit address will come here at AD7 and AD0. It will come here at AD7 and AD0. It is not a 16-bit address. The higher order address bus, there will nothing be at the higher order address bus. This address will come at AD7 to AD0. Then using this latch, this address will get latched here. This address will get latched here. This address will get latched at a lower order address bus A7 to A0. A7 to A0. Now see, this A7 to A0 is connected with this AND NAND gate through hardwire. This A7 to A0 is connected with a NAND gate through hardwired. So the output of this NAND gate will be 0, and this input device will get enabled. This input device will get enabled. Here ALE is 1. Here ALE is 1. Now we have to give control signal also, so that we have to give a control signal also. So we have to read data from input device. So we will have something like this: 1 0 1. So when 101 will be present at the control pins, then the input output read command will be activated. And now the data which is present at this memory this input device and at memory location 77H that will be read, and this data will come into the microprocessor through this path, and this data will come into the microprocessor through this path. Here the data will not get coincide with 77H with 77H, because by this time ALE has become 0. So So this data get latched at the output of latch module, and this data will come here and it will go here, because now this AD7 and AD0 is acting like a data line, So this is how a microprocessor reads data from input device. Now suppose we want to write data into output device. Now suppose we want to write data at output device. Now suppose we want to write data at output device, then see again same thing will happen. First our ALE will be 1. Our ALE will be 1. So this 77H, which is at a lower order address line here, it will get latched with and it will come here, now this is connected with this NAND gate. And so its output will be 0, and this my now it is my output device. Now this is my output device, and output device will get activated. So now if we want to write data at the output device, then we use out instruction. For reading data, we were using in instruction. For writing data into output device, we will use out instruction. So what is the meaning of this instruction? Meaning of this instruction is that microprocessor wants to write data at a output device at a memory location FFH, So now this output device is activated, but now we want to write data into this. So the status of control signals will be something like this. Status of control signals will be something like this. It will be 110. So now our input output read control signal will get activated, and now the data which is at a microprocessor will come and it will get stored in the output device using this path. It will come and it will get stored in this output device using this part, because now this AD7 and AD0 is acting like a data bus, and this low order address, that is 77H, is already latched here, because by this time ALE has changed from 1 to 0. ALE has changed from 1 to 0. ALE has changed from 1 to 0. Fine. So this was all about the concept of peripheral mapped input output. So this was all the concept of peripheral mapped input output, in which microprocessor is communicating with input device and output device, and how it is mapping with input and output device is demonstrated here. So we talk about if we talk about the properties, some of the properties, some of the properties of if we talk about some of the properties of peripheral mapped input device. So if we talk about some of the properties of peripheral mapped input output, then what will be it? So for first property, microprocessor, for peripheral mapped input output, microprocessor deals with 8-bit address. It deals with 8-bit address. It doesn't deal with 16-bit address. It deals with 8-bit address. Because for communicating with input output device, we only need 8-bit address. For communicating with memory, we required 16-bit address. Now second one is the two important instructions in peripheral mapped input output is in and out instruction. Two important instructions in peripheral mapped input output. are in and out instructions, are in and out instruction. The third property is that for peripheral mapped input output, microprocessor can generate 256 addresses, 256 addresses, 256 addresses separately for input and output device, separately for input and output device, for input and output device, for input and output device. See, um, we had 8-bit address, we had 8-bit address while dealing with peripheral mapped input output. So 2 to the power 8 is 256. So microprocessor can generate 256 addresses. Microprocessor can generate 256 addresses. Now see, we have two different control pin. We have two different control pin. One is the input write pin, and other is it's one is the input read pin and another is input write pin. That's why we can generate 256 separate addresses, 256 addresses, 256 address for input device, for input device, and 256 address and 256 address for output device, for output device, 256 address for input device, 256 address for output device. Suppose we had only one control pin, suppose we had only one control pin, something like input output read write. It is the it is just hypothetical, don't remember it. In that case, if we would have used this pin only one control, if we had input output read control signal, and using this control signal we would have communicated with input as well as for output devices, then we would have got 256 total addresses for input output. We would have got 256 total addresses for input as well as for output, for input as well as for output. But here we have two separate control signals. So microprocessor can generate 256 separate address for input and 256 separate address for output. This is important, this is important, and this sorts of questions are asked in exam. First they will ask you that in peripheral mapped input output, in peripheral mapped input output, 8-bit addresses or 16-bit addresses are used. So its answer will be 8-bit address. Then second question may be that what are the instructions used for peripheral mapped input output. They will give you in instruction, out instruction, STA, LDA. Then its answer will be in and out. Then third and the important one will be that in peripheral mapped input output, how many addresses a microprocessor can generate for input and output devices. Then we can say that it is 256 each, that is 512 in total. So this was all our properties of peripheral mapped input output. So now see another important concept we will see here. So I told you that for dealing with the input output device, we require only 8-bit address, and this 8-bit address get latched here, and then finally it comes at the lower order address line. So you will say that, sir, by this time, by all this process, what will happen to higher order address line? What will happen to higher order address line? Will it remain idle, or what data will be stored there, and what it will do? Yes. Then its answer is that during all this process, when the 77H was latched here, and then it was latched here, and then it came to this input output device, and everything was going on. This 77, the higher order address line, or we can say this 77H address, this 8-bit address 77H will also get copied, at this, that is at higher order address line. will also get copied will also get copied at this higher order address line, will also get copied will also get copied at higher order address line, at higher order address line. Then see, from here we can discuss one important condition or concept also. So what I am saying is that if we are having an instruction in 77H, we are having an instruction in 77H, then this 77H address will also get copied at higher order address line. That is, we have an option that by connecting this higher order address line with this NAND gate, by connecting this higher order address line with this NAND gate, we can achieve the result which we were achieving by connecting lower order address line by this NAND gate. See, can why can't we achieve it? If we get this address copied here, and in this NAND gate, if the manufacturer applies inputs A15 to A8 instead of A7 to A0, then again the same thing will come, again the same thing will happen. This 77H will enable this input device, and the control signals we are already having input output, right? So the data will come here, so the data will be read and it will come here. So what will be the benefit of this? What will be the benefit of using higher order address line with while dealing with input output device instead of using lower order address line? And the benefit is that in this process we don't require latch. In this process we don't require latch. In this process we don't require latch. For enabling input output device, we can use higher order address line, and for bringing the data to microprocessor we can use this path, and this latch would have got bypassed. So for dealing with input output device, manufacturer has two way, that is that they can either use higher order address line in which latch get bypassed, and or we can use lower order address line in which latch is included. So this is another important concept of using peripheral mapped input output, which you should keep in mind. So see, by this concept, what I am telling you is that if I write it as A15 to A14, 13, 12, 11, 10, 9, 8, and here we will have A7, A6, 5, 4, 3, 2, 1, 0. So in this case, what I told you that in the first case, the address as at lower order address line was 77H. Okay, fine. 77H, so it will be 1111111. Then again I told you that in microprocessor what it happens is that while dealing with input output device, this address 77H also get copied to higher order address line. It means here also we are having the same thing. Here also we are having 77H. Here also we are having 77H. Here also we are having 77H. Okay, fine. Now see one interesting thing. Suppose this arrangement is given to you, and in this NAND gate, this all inputs are applied. Okay, 8 address lines, 8 address lines, 8 address line. So the input of NAND gate has this 8 address line, but here you can see that I have not used A15 to A8 in continuation, or I have not used A7 to A0 in continuation. I have used A15, then A14, then A5, then A12, then A3, then A10, then A1, and then A0. Then see, now if microprocessor wants to perform a input read operation, if it wants to perform input read operation, and if you are given an instruction like this, in again the same instruction in 77H, that is microprocessor wants to communicate with input device and it wants to read data which is at memory location 77H of input. So if we give this inputs at the input of NAND gate, then will it work? Then will it work? Then will it work? Very important, very important. Listen to it carefully. Then will it work? I will say yes, it will work. See how? I told you that this 77H will come here, and this same address 77H will also get copied at higher order address line. Fine. Then here I am having A15, then A14, then ideally here we should have got A13, but I have written A5. See, what is value of A13? 1. What is value of A5? 1. So whether it will make any difference if I connect A13 address line or I connect A5 and address line? No, there will be no difference. Now again A12, okay, then I have connected A3. I have connected A3. Now see, what is the value at A11 and A3? It is same. It is same. So will it make any difference if I connect A3 instead of A11? No, it will not make any difference. Then it is A10 and then A1 and A0. A1 and A0. See what is the value of at address line A9 and A8, and what is the value at address line A1 and A0. It is same. So will it make any difference? No, it will not make any difference. So this arrangement, it will work properly. Absolutely it will work, and we will get the desired result, and we will get the desired result. So these are the concepts. These are the concepts which you should study, and you should have and hold on it, because in gate exam this type of concepts are only used. This type of questions are only framed in which if your concept is weak or not clear, then you will not be able to solve the question. See what question can be asked in gate exam. What questions can be asked in a gate exam? In this architecture only, suppose one arrangement would have been given like this. One arrangement would have been given like this, in which the inputs at NAND gate would have been A15, 14, 5, 12, 3, 10, 1 and 0. And in another and you would have been given one another diagram in which they would have given the inputs of NAND gate like this: A15 to A8, and they would have given you another diagram, and they would have given the connections like this: A7 to A0, A7 to A0, A7, A7 to A0, A7 to A0. Then they would have given you this instruction in 77H, and the question would have been asked was that in using which arrangement microprocessor can read data which is present at memory location 77H. Then most student would have suppose that this is option A, it is B and C, and options given are only A, only B, only C, only PC, only AC, and ABC. Means you will not get more than four options, but I am just taking it with what all possibilities can be there while framing the questions. So most of student would have picked C because they would have thought that microprocessor has to deal with input output device, and for dealing with input output device we only need 8-bit address, and that 8-bit address will only come at this lower order address line, that is at A7 to A0. Then another set of student who had a concept slightly better than this, then they would have thought no, this 7 address also gets copied with higher order address line, so A15 and A8, this will also work. But the students who know this concept, that what are the values at this and what are the values or at this, so if the values at this are same, then we can use any one of it, then those students will pick the answer as ABC. Those students will pick the answer as ABC. So this was all the concepts which I wanted to tell you regarding peripheral mapped input output. Regarding peripheral mapped input output, I also discussed with you that what type of questions can be asked in various exams. So I think now it is clear. Now I will discuss with you the memory mapped input output. Now I will discuss with you memory mapped input output. Now, when we have learned all the concepts, so let's take an example. So let's take an example and summarize everything. And summarize everything. If you have missed any part or if any concept is not clear in earlier portion, then listen to this part nicely. I'm going to summarize all the concepts. So if anything is missing, then you can cover it up. You have one more option of covering it up. And after discussing this example, we will discuss one important concept, that is peripheral mapped input output and memory mapped input output. And that concept is dependent upon this summarization. So please listen to it carefully. So please listen to it carefully. So here I am going to again demonstrate you that how microprocessor communicates with memory and how microprocessor communicates with input output devices. Input output devices. So let first we will deal with memory. Here we are having two memory. This is the first memory. This is the second memory. Here we can see that in the first one, memory read operation is taking place. Here in the first one, memory read operation is taking place, and in the second memory, we can see that memory write operation is taking place. Memory write operation is taking place. So first, let's see what is the range of this to memory. First, see what is the range of this to memory. Suppose I keep everything same. Here also A7 to A0. Here also A7 to A0. And here it is A15 to A8. And here it is A15 to A8. And the output is coming through a NAND gate. Output is coming through a NAND gate. And it is active low. Chip select. Active low. Chip select. Then say what will be the range? What will be the range? What will be the range of both memory locations? What will be the range of both memory? What will be the range of both memory? It will be 0, 0, 1, 1, and here we will have all 1, here we will have all 1, so it will be something like this. It will be something like this. It will be something like this. Or I can write it like this way also. FF00 to FF11. This is range of both memory. This is range of both memory, because we are taking it same. Everything is same. The arrangement of address and the arrangement of data line is same in both this memory. Okay, fine. Now suppose microprocessor. Now suppose microprocessor wants to communicate. Now suppose microprocessor wants to communicate with memory location FF01H. It wants to communicate with memory location FF01H. Then see what will happen. I told you earlier that the higher byte, that the higher this. I told you earlier that this higher bit, that this higher bits will come at a higher order address line. See, this address line is connected with this also, hardwired, and this address line is connected with this also. Let me draw it with another color. Yes. This address line is connected with this also. This higher order address bus is connected with this memory also. This higher order address bus is connected with this memory also. So I told you that the higher bit, that is FF, FF will come here, FF will come here, and FF will also come here. FF will also come here. Fine. Then simultaneously ALE will be energized. ALE will be my 1. ALE will be energized. That is, it will be 1. So now my lower bits. So my lower bits, which was earlier stored here. My lower bits which was earlier stored here. My lower bits which was earlier stored here, it will come here. It will come at A7 to A0. It will come at A7 to A0. It will come at A7 to A0. Okay, fine. Now this lower order address bus is connected with this. Lower order address bus is connected with this. And this lower order address bus is also connected with second memory. It is also connected with second memory through hardwired. Through hardwired. Through hardwired. Okay, fine. So now you will say that, sir, this FF01 address is in this memory also and in this memory also. So simultaneously both memory will get activated. So simultaneously both memory will get activated. So simultaneously both memory will get activated. No, it is not the case. It is not the case. Why? Suppose that microprocessor wants to read. Suppose microprocessor wants to do read operation from memory. Suppose microprocessor wants to do read operation from memory. So what will be the status of control signals? What will be the status of control signals? Here it will be 0, it will be 0, and it will be 1. So by using 0, 0, 1, my memory read uh, my memory read control signal will be activated. Only my memory read control signal will be activated. And see, here we are having memory read, here we are having memory read, but here we are having memory write. So it will get activated or it will get enabled, but it will remain disabled or deactivated. But it will remain disabled or deactivated. So see, here I am going to give you an important concept that while choosing memory, or I can write it like this, or while interfacing interfacing with memory, three things are important for a memory to get selected or not. Three things are important for a memory to get selected or not. Three things are important. Three things are important. Three things are important for a memory to get selected or not. Three things are important for a memory to get selected is or not. First is higher order address line. First is higher order address line. Second is lower order address line. Second is lower order address line. Third is control signal. Third is control signal. Third is control signal. Third is control signal. When the data or output of all these three will match according to our desired operation, when output of all these three will match as the as our desired operation, then only that memory will get selected, otherwise it will not get selected. Suppose if I talk about the higher order address, if I talk about the higher order address line, so here I told you that its address is FF, and here also its address is FF. Fine. Now I will delete it. Now suppose what I will do, suppose I put a inverter here. I put a inverter here. So what will be its address? Its address will become FE, and its address will become remain FF. So now for microprocessor whose higher order address bus is connected to this and this also through hardwired, but while interfacing, this will be disabled, and while interfacing, and if we want to interface with memory location FE, let lower bit be anything, let lower bit be anything, then microprocessor, then this memory will get activated and this memory will not be activated. Okay, fine, because my higher order address is different. Here it is FE, here it is FF, but we want to communicate with FE, okay, this is the first scenario. This is the first scenario. Now if I talk about the second scenario, suppose here we are having A7, here we are having A7 to A0, here we are having A7 to A0, here we are having A7 to A0, here also we are having A7 to A0 as a lower order address line, as a lower order address line, as a lower order address line, as lower order address line. Now suppose we would have got something like this. We would have got something like this. This would have become A6. This would have become A6, and this would have become A7. This would have become A7. So now see what would have happened. My higher order address as well as lower order address of this would have been completely different as compared to the higher order address as well as lower order address of this. So again, though the microprocessor is connected with both this memory through hardwire, but at a time only one memory would have been selected based upon the memory with which memory address with which microprocessor wants to communicate. Okay, now coming to the third one, coming to the control signals that we saw earlier also. Suppose everything would have been same. Suppose everything would have been same. Suppose everything would have been same. It would have been A15 to A8, and this also would have been A15 to A8, A15 to A8, and this is A7 to A0, and here also A7 to A0. Then in this case, the higher order as well as lower order would have been same. The higher order as well as lower order address would have been same, but still only one would have been activated because it will depend upon the control signal. That is, either we are doing memory read operation, or we want to do memory write operation, because microprocessor at a time can perform only one function. It cannot perform two functions, so both would never have been selected. Both would never have been selected. So I think that now the concept is further clear to you, and if there would have been any missing part in your concept, then you would have filled it up. So this is the way how microprocessor communicates with memory. Now, in the same way, if we want to see how microprocessor communicates with input-output device, how microprocessor communicates with input-output device. So see, for while communicating with the memory, microprocessor generates a 16-bit address. But while communicating with input-output device, only 8-bit address is required. Only 8-bit address is required. Only 8-bit address is required. Fine. Then see, suppose here what we are having. We are having two input output devices. Here we are having two input output devices. Here the addresses, low order address is A7 to A0. It is A7 to A0. So what will be, suppose what will be the range of this? What will be the range of this? This would be FF. If I take everything 1 year, it will be FFH, and similarly it would also be FFH. Okay, fine. Now microprocessor wants to read data from memory location FFH. Microprocessor wants to read data from sorry, not from memory location, but from input device, having address FFH. Microprocessor wants to read data from a memory location FFH of input device. Microprocessor wants to read data of memory location FFH from a input device. So see, we are having two instructions in microprocessor. In instructions part, we are going to see everything in detail, but here I just want to show you this concept. So I want these two instructions. Suppose we have in FFH. This instruction means that microprocessor wants to read data which is present at 8-bit memory location FFH of the input device and bring it back to microprocessor. Similarly, while communicating with output device, there's a instruction out FFH. What is the meaning of this out FFH? Its meaning is that microprocessor wants to store data at memory location FFH of output device of a output device. Fine. So first we will see in operation. First we will see in operation. So we microprocessor want to communicate with the memory location FFH. So it is having only 8 byte. So this FF will come here. This FF will come here. This FF will come here. This FF, this FF will come here. Now ALE will be energized. ALE will be energized. So this FF will come here. This FF will come here. Now this A7 to A0 is connected with this also, and this A7 to A0 is connected with this one also. Is connected with this one also. But this will be activated, this will not be activated because we want read operation, because we want a read operation. So if we want a read operation, then what will be the status of our control signals? So what will be the status of our control signals? The status will be 1 0 1. In this case, only input output read control signal will be activated, and it will remain deactivated, so it will not be selected. So now once it is activated, now the data will be read. Data will be read, and this data will come to the microprocessor from D7 to D0. It will come to microprocessor from D7 to D0, and following this path, it will go inside the microprocessor. Following this path, it will go inside the microprocessor. There will not be interference of this data and FF, because by this time ALE is disabled. ALE is disabled. That is, ALE has become 0. So as ALE has become 0, this FF will remain latched here at the output. This FF will remain latched here at the output, and this data will come from here to here. This data will come from here to here. Now, similarly, if we want to write data into a memory, if we want to perform out operation, then similarly, this low order address will come here. ALE will be enabled again. ALE will be enabled. Again, ALE will be enabled. FF will come here. FF will come here also. FF will come here also. But this time this will not be activated because we want to perform memory read. So what will be the status of control signal? It will be 110. So this will get activated. Now this is activated. Now we want to write data into here. So the data from memory will follow this path. And it will come here. Again, there will be no interference of FF with the data coming out of microprocessor, because by this time ALE has become disabled. So this FF will get latched here, and this data following this path will come here, and it will get stored in our memory. So this I have given you one overview that how exactly microprocessor is interfacing with memory as well as input output device, input output device. So I think now everything is crystal clear to you, and you have understand all the concept of it. Now there are two important concepts related to memory mapping. So let's quickly cover these two concepts, and then we will move forward for instruction set. So first one is finding starting and ending address for memory chip. Suppose you are given a memory chip, you are given capacity of that memory chip, and then you are also given its starting address, and you are asked to find its ending address, or you are given the ending address and you are asked to find the starting address. This type of questions also becomes a part of memory mapping. So what we have to do for it? So there are two steps. So first take an example. We will understand this step through a example, because if we will take up this step, then you will not understand that what I am trying to tell you. So let us see this concept through an example. So see, here what it is given. Here it is given that we are having a ROM. We are having a ROM whose capacity is 4 KB. We are having a ROM whose capacity is 4 KB. And it is also given that starting address is 8C4EH. Starting address is 8C4EH. And we are asked to find the ending address. We are asked to find the ending address. So see, what will be our approach? Step 1. Step 1 is to find number of address line. Step 1 is to find number of address line. We know the formula. 2 to the power n is equal to big N, where big N signifies the capacity, and small n indicates number of address line. Number of address line. So if we talk about this, then it will be 2 to the power n is equal to 4 kilobyte, is equal to 4 kilobyte. So it will be 2 to the power 2 into 2 to the power 10 into 2 to the power 10 byte. So it will come out to be 2 to the power 12 byte. 2 to the power 12 byte. Therefore, n or number of address line is 12. N or number of address line is 12. Now coming to step 2. Now coming to step 2. Now we will represent this number of address line with equivalent 1. With equivalent 1. That is, there are 12 address line. So we will write 12 times 1. We will write 12 times 1. If n would have been 13, then we would have written 13 times 1. Then we would have written 13 times 1. See what it is written in step 2. What it is written in step 2. See, this is our step 2. Put equivalent number of ones. See, first step is find number of address line according to the capacity of memory that we have found. That is n is equal to 12 for this question. Then second step is put equivalent number of ones as that of address line and find hexadecimal value. Put equivalent number of ones as that of address line and find hexadecimal value. So that's why we here n is equal to 12. So we are representing it or putting it with we are representing it with 12 equivalent ones. 12 equivalent ones. Now we have to convert it into hexadecimal. Now we have to convert it into hexadecimal. Now we have to convert it into hexadecimal. So what we will get? We will get it like FFF. FFF. Okay. We have converted it into hexadecimal. Now see. Then add or subtract to get ending or starting address. Add or subtract to get ending or starting address. That is, here see what it is given. Here it is given starting address is this. We have to find ending address. We saw in memory mapping that the range always starts with 0. If n is 1, we have seen that if n was 1, then starting range was 0, end in range was 1. If n was 0, start in range was 0 and end in was 1 1. So it is always in increasing. So now if it is given that the starting address is this and we have to find ending address, means we have to add this. We have to add this equivalent, then only we will get the ending one, because ending will always be greater than the starting address. Similarly, if suppose you are given ending address and you are asked to find starting address, suppose you would have been given here that this is the ending address and we would have been asked the starting address, then we would have subtracted, this to get the starting address, because starting address is always lesser than the ending address. Fine. So here starting is given 8C4EH, 8C 4EH, and here we have found it as FFF. It is of 16 bit, it is of 12 bits, so we will consider the remaining 4 bit as 0. Remaining 4 bit as 0. Now we have to add it. To get the ending address, and on add-in we will get it like 9C 4DH. I am not going to solve it. You can solve it on your own. I am just directly writing the answer. This is my ending address. This is my ending address. This is my ending address. So it is simple. What we have done, first we have found number of address line. First we have found number of address line from the given capacity. Then we have represented that address line into equivalent 1. Then we converted it into hexadecimal. Then we had the starting address, so we added it to get the ending address. If this would have been our ending address, then we would have subtracted it to get it the starting address. Easy. Now see another question here. Find starting address. Okay. Say here the capacity is given 4 KB. Here ending address is given. We have to find the starting address. See. So first we will find the number of address line. So here we will get 2 to the power n, 2 to the power 3 into 2 to the power 10 byte. So we will get n is equal to 13. Now we will represent it with equivalent 1. So 13 1. Now we will convert it into hexadecimal. We will get F. We will get F. We will get F. Here we will consider 0 0 0. If nothing is there, then we will consider it as 0 0 0. 0 0 0. So it will be 1. Now what it is given? It is given the ending address is this. So the ending address is this. Ending address is this. Now we have to subtract it to get the starting address. We have to subtract it. We have to subtract it to get the starting address, and we will get the answer. We will get the answer as 4A. I am not solving it. You can solve it. 4A 3CH. 4A 3CH. This is my starting address. This is my starting address. So it is easy. Just keep one trick in mind. Just keep one thing. Just keep one thing in mind. Just keep one thing is just keep one thing in mind. Just keep one thing in mind. That is, always keep this capacity. Always keep this capacity. Just keep one thing in mind. Always keep this capacity in bytes. Always keep this capacity, memory capacity, in bytes. Always keep this memory capacity in byte. Don't convert it into bit. Don't convert it into bit. See how the gate examiner will try to trick you. Here it is given 4 kilobyte ROM, so it is okay. It is already in byte, and when we have converted, we have kept it in byte. In gate, you will get an question where you will find capacity as like this. It will be given something like this. They will give you. They will give you like this. They will give you right there like this. Here it will not be written anything. Bit or byte, it will not be written. But we should know that this is in bit. We should know that this is in bit. So we will ignore this. It is not that while finding the address line, we will do 2 to the power 12 and 2 to the power 3. And finally, we will get 2 to the power 15. And we will say that n is 15. No, it is wrong. It is wrong. It is wrong. We will not convert it into bits. We will not convert it into bits. We will keep it in bytes only. We will keep it in bytes only. We will keep it in bytes only. So keep this trick in mind. Keep this trick in mind. Otherwise, you will commit mistake. So if it is given 2 to the power 12 into 8, then we will know that it is in bits. So we will consider only 2 to the power 12. Then n will become 12. Similarly here, if we are given like this, then they will give it like this 2 to the power 13 into 8. Then we will ignore this. We will only take 2 to the power 13, that is n is equal to 13. So I can write it like this. Always keep memory capacity. Always keep memory capacity in bytes. Important. This is important while solving such type of questions. Rest part is easy. You will, if you will get confused, then you will get confused in this part only. So keep this in mind. A small concept related to memory mapping, which we should know is that how to find number of chips required to design memory with available memory or capacity. That is, if you are asked that suppose you are given XYZ memory capacity, XYZ memory capacity is available with you, and ABC memory capacity is required to be designed by you, and you need to design ABC capacity memory. Then how you can how many will be the number of chips required? Then how many will be the number of chips required? So in this case, number of chips required will be memory to be designed by memory to be available. Memory to be designed by memory available. Easy. There's no need to go much in details of it, because here you will get direct questions and you have to just put it into the formula and get the answer. So let's suppose we have got a question like this. Calculate number of this RAM chips required to this design. This means what we have to design. We have to design 8 kilobyte. What we have to design? We have to design 8 kilobyte memory. And what memory is given to us? 256 cross 8 RAM memory is available with us. So it is asked that what will be the number of chips required. So number of chips required, number of chips required, this will be equal to memory to be designed, memory to be designed, memory to be designed by memory available, by memory available. See, here also you have to keep a short trick in your mind, and that is always bring this memories into bit. That is, memory to be designed, it is given 8 kilobyte, convert it into bits, number of bits. And here memory available is 256 cross 8, so it is already in bit. In the previous concept, I told you that always keep memory capacity in byte. Always keep memory capacity in byte form. And here I am saying that while calculating number of chips, always convert memory capacity into number of bits. So by doing so, you will never commit mistake, because in gate exam you will get uh, tricky memory capacity. Not tricky, they will just try to confuse you. So always keep it in bits. So here it is given 8 kilobyte memory is to be designed. So if I will convert it into bits, then it will come to be 2 to the power 3, 2 to the power 10. This is 8 kilobyte. Now I will do into 8. This is converted into bits. 8 is converted into bits. Now memory which is available with me, it is already in the form of bit, that is 256 into 8. Then see what will be my number of chips required. Here we can write it as 2 to the power 8, then 13, 13 and 8, 5 means 32. 32 chips will be required. 32 chips will be required. So it is easy. Memory to be designed given, memory available given, convert it into bits, divide it, you will get the answer. That is number of chips. See here also number of chips are asked. So what we will do, memory which is required to be designed is 16 kilobyte. So 2 to the power 4, 2 to the power 10, converted into bits into 8, it is in bit. And the memory which is available with us is already in the form of bit. The memory which is given available with us is already in the form of bit. So what it will become? It will become 17, and it will become 11. It will come out to be 2 to the power 6. That is 64 chips. That is 64 chips. So here also you can write one short trick, that is always convert memory to be designed and memory available in bits. In previous, in the starting address and ending address, I told you to convert it into byte, and here I am telling you to convert it into bit. So you will not make mistake. So this was all about our memory mapping. We have seen some very important concepts, very important short tricks, and now you have an overview of how memory, how microprocessor works, how microprocessor communicates with memory devices and input output devices. Then what is difference between peripheral devices, mapped input output, and memory mapped input output. So after knowing this all concept, now when we will move into the instruction set and how different instructions are executed, then you will easily understand, because now you know the working of microprocessor to a very large extent. Now coming to the pin diagram of 8085 again. So see, this all pin which are marked in red color, we have already discussed. We have already discussed, and we have discussed it in details. We have discussed it in details. So now we will discuss some more pins of 8085. Now we will discuss some more pins of 8085, and let's see what are the significance of this pin. So today we will discuss. So today we will first discuss this two pin, that is hold and HLDA. We will discuss this two pin, that is hold and HLDA. Okay. So see, with hold and HLDA, we will discuss one very important operation which is known as the DMA operation. Full form of DMA is direct memory access. Full form of DMA is direct memory access. Full form of DMA is direct memory access. Direct memory access. Direct memory access. So see, what is the function of DMA? Suppose there is a huge data. Suppose there is huge data and that data has to be transferred from memory to input output devices, and that too at a high speed, suppose we have a huge data and that data is to be transferred from memory to input output devices, or from input output devices to memory, or from input output devices to memory, and that too at a fast rate. Then if we try to perform this transfer of data through microprocessor, then we can achieve in transferring data, but we cannot achieve speed. This transfer will take time, and if time is the most important factor, as time is most important factor in everyone's life, so if time is an important factor, then we would not prefer this path of transferring data through microprocessor. In that case, DMA will come into picture. That is, in that case, a DMA controller will come into picture. So see what will happen. If we want to transfer large data at a high speed between memory and input output device, then DMA controller will send an input signal hold to microprocessor. It will send an input signal hold to microprocessor. So hold is active high. Hold is active high input signal. Active high input signal to microprocessor. Active high input signal. Active high input signal to microprocessor. To microprocessor. So DMA controller will send an active high input signal to microprocessor, and that is hold. And by sending this hold, DMA controller will request microprocessor to transfer control of all buses, that is address bus, data bus, control bus. It will request microprocessor to transfer control of all buses to DMA controller. Then see what microprocessor will do. First of all, microprocessor will complete its ongoing work. First of all, microprocessor will complete its ongoing work, and then it will send an output signal to DMA controller, and that is hold acknowledgement. That is, by sending this signal to microprocessor has agreed, and microprocessor has transferred control of all buses to DMA controller. Microprocessor has transferred control of all buses to DMA controller, and it is also acknowledged by microprocessor by sending HLDA to DMA controller. So if we talk about HLDA, it is active high. It is also active high output signal. Output signal from microprocessor. Output signal from microprocessor. Output signal from microprocessor. Okay. Then what will happen? Then DMA controller will control all the buses, and data transfer between memory and input output device will start. It will start, and once all the data transfer process has completed, then this hold signal will be pulled down by DMA controller. Then this hold signal will be pulled down by DMA controller, and the control of all buses will again go back to the microprocessor, and the control of all buses will go back to the microprocessor. So I think this function of hold and HLDA is clear. It is a active input signal. It is active output, active high input signal. It is active high output signal. Then we have seen what is the function of DMA controller. And so if we take a question, suppose we have a question like this. In DMA operation, in DMA operation, in DMA operation, data transfer, data transfer, data transfer takes place between, one is memory and microprocessor, second is input output and microprocessor, third is memory and input output device, and the last one is none. So what will be your answer? So what will be your answer? In DMA operation, we have discussed that data transfer takes place directly between microprocessor and input output device without any interference of microprocessor. In DMA operation, data transfer takes place directly between in DMA operation, data transfer takes place directly between memory and input output device. Data transfer takes place directly between memory and input output device without any interference of microprocessor, without any interference of microprocessor, without any interference of microprocessor. Now there are two types of mode in DMA operation. There are two types of modes in DMA operation. There are two types of modes in DMA operation. There are two types of modes in DMA operation. First one is burst mode. First one is the burst mode. First one is called the burst mode, and the second one is known as the cycle stealing. Second one is known as the cycle stealing or short burst mode or short burst mode. So see what is difference between these two mode of operation. What happens in burst mode is that DMA controller sends a hold signal to microprocessor, and DMA controller gets control of all the buses of microprocessor. Now the data transfer between memory and input output device will start, and it will complete, that the whole data transfer will take place at a once. Whole data transfer will take place at a once, and once whole data transfer has taken place, then DMA will pull back its hold signal. Then DMA will hold back its hold signal. Example is data transfer. Data transfer. Data transfer in hard disk. Data transfer in hard disk. In this, once DMA has the control of all the buses, then the complete data transfer process will take place. Only then the control of addresses only then the control of buses will be given back to microprocessor. But what happens in cycle stealing or short burst mode? Here, the data is divided. Here, data is divided into several blocks. Data is divided into several blocks, and these blocks these blocks get transferred between memory and input output devices at a particular instant of time. That means the transfer of data is not continuous. The transfer of data between memory and input output device is not continuous. It is a kind of discrete transfer. So whenever the transfer of data, or whenever transfer of these blocks takes place between memory and input output device, then DMA has the control of all the buses. But once one complete block of data get transferred between memory and input output device, then DMA gives back the control of buses to microprocessor. So in the meantime, microprocessor can complete its work, and then again when another block of data is to be transferred between memory and input output device, then DMA again request back the control of buses. So in this, complete data is not transferred between memory and input output device at a once. Chunks or blocks of data are transferred at different instant of time. So by doing this, the efficiency of microprocessor increases, because say if data transfer takes place 1 hour of time, then in this case the microprocessor will remain idle for 1 hour of time. But here, if it will take 1 hour for data transfer to take place between memory and input output device, then in those 1 hour maybe microprocessor is able to work for 30 minutes, and for remaining 30 minutes this blocks of data is getting transferred. So this was all about DMA operation. So this was all about DMA operation and the uses of our two control pins, that is hold and HLDA. Now, again coming back to pin diagram of 8085. So now we have seen hold and HLDA. So now there's one other pin, VCC. Here input supply is given to microprocessor. Here input supply is given to microprocessor, and it is generally 5 volt. And it is generally 5 volt. That is, microprocessor works at 5 volt input signal. This figure is important for PSU exams. They may ask you that what is the operating voltage of microprocessor, then it is 5 volt. So this is the VCC pin. Now coming here to this VSS pin, this is the ground pin. This is the ground pin. This is the ground pin. So here we are applying input. Here we are taking the here we are grounding the microprocessor. Here we are grounding the microprocessor. Now see, here we have an active low. Here we have an active low input signal, that is reset in. It is active low input signal. 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 Reset in. Reset in. So it is used to reset microprocessor. It is used to reset microprocessor. Now we have another pin, reset out. So when microprocessor is resetted by reset pin, then it sends an acknowledgement from reset out pin. It is an output pin from microprocessor. It is an output pin from microprocessor which is giving the acknowledgement that microprocessor is resetted. It is also used to reset input output device. It is also used to reset input output device. It is also used to reset input output device. Now coming to this pin, ready pin. Now coming to this pin, ready pin. See, many peripheral devices are connected with microprocessor. Many peripheral devices are connected with microprocessor. So, suppose we have a printer connected with microprocessor, and microprocessor has given command to printer to print 1000 pages. So, to print 1000 page, printer will take some time. But now suppose after 1 minute, microprocessor again sends a command for printer to print another 2000 pages. So the printer will get hanged because the speed of printer is not the same as that of the speed of microprocessor. So we use an pin known as the ready pin. It is an input signal. It is an input pin or input signal to microprocessor from slow peripheral devices. From slow, from slow peripheral devices. From slow peripheral devices. From slow peripheral devices. Slow peripheral devices. So when ready pin is high, so when ready pin is high, it means that slow peripheral device is ready to take command from microprocessor, and when it is low, then it means that peripheral devices, slow peripheral devices are not ready to take command from microprocessor. Okay, this is completed, this is completed, this is completed. So now coming to x1, x2. So now coming to x1, x2. In between these two pins, x1, x2, a crystal oscillator is connected. A crystal oscillator is connected to generate reference frequency. To generate reference frequency. We are using crystal oscillator because it's provide stable oscillations. RC or LC oscillators are temperature dependent. They are temperature dependent, so their oscillations are not stable. So we use a crystal oscillator. So we use crystal oscillator in microprocessor. So we use crystal oscillator in microprocessor to generate a reference frequency. To generate a reference frequency. Now in microprocessor, there is a clock generator. Now in microprocessor, there is a clock generator. Now in a microprocessor, there is a clock generator which take this reference frequency and it divide it by 2. It take reference frequency, it divide it by 2, and this frequency is known as the operating frequency. This is known as the operating frequency or clock frequency or clock frequency or clock frequency. So here we can take a formula. So here we can take a formula f clock or f operating is equal to f crystal by 2, f crystal by 2, f crystal by 2. This f clock is generally 3 megahertz. This clock is generally 3 megahertz. That is, microprocessor works at 3 megahertz operating frequency. It works at a 3 megahertz operating frequency. So if this is 3 megahertz, that is the crystal oscillator must have generated 6 megahertz. That is f crystal would have been, that is f crystal would have been 6 megahertz, would have been 6 megahertz, would have been 6 megahertz. So here we have a one simple basic formula. F clock or f operating is f crystal by 2, f crystal by 2. Then we have a clock out. It is used to take this, it is used to take this operating frequency or clock frequency to input output devices, to input output devices, to input output devices. So input output devices. Two input output devices. So see what all pins we have covered. We have covered this VCC, HOLD, HLDA, clock out, reset in, ready, input output, status signal, uh, read bar, write bar. This is again our status signal. This is again our status signal. These are our address line. These are our address line. These are our address line. These are our data lines. These are our data lines. Then reset out x1 and x2. So now this is left. This portion is left. This is mainly our interrupt portion. This portion is left. This is mainly our interrupt portion. This is mainly our interrupt portion. This is mainly our interrupt portion. So now see, now you must be getting this pins of microprocessor on your tips. The way we have divided this pins into different categories and then we discussed it one by one in details. Now you can easily memorize all this pin and you don't need to just mug it up. So now next we will see the interrupts. Now next we will see the interrupts of microprocessor.